Hey guys, tonight we begin a journey together, exploring a world so alien yet so fundamental to our existence that it challenges everything we think we know about our planet. This is the story of Earth as it existed 3 billion years ago, a world of impossible colours, strange chemistry, and life forms so different from anything alive today that they might as well have come from another planet entirely. If you're enjoying this journey through deep time, I'd love to know where in the world you're listening from tonight. Are you drifting off in a bustling city, or perhaps in some quiet corner of the countryside? The same atoms that compose the ancient atmosphere may currently be part of the air you're breathing, having been recycled through 3 billion years of planetary circulation. Welcome to a time when the Earth was still figuring out how to be itself. Imagine going outside on a clear night for a moment, with your eyes closed. The same stars that have watched over Earth for billions of years are still dancing across the dark sky above you. Now let yourself go back in time, not just decades or centuries, but 3 billion years. What would you see if you could stand on that old Earth and breathe in air that had never smelled a flower or heard a bird sing? The sky would be the first thing that would catch your eye about this old Earth. Forget about the bright blue dome we see today. 3 billion years ago, the air on Earth was a painter's palette of oranges, pinks and deep purples that changed and swirled like the northern lights, but stayed the same all the time. The air was different too. It was thinner and had only about 20% of the oxygen levels we have now. You couldn't have lived here without a breathing device, but the life that did exist here thrived in ways that seem almost magical to us now. The sun, which has always been there for us, was about 25% dimmer than it is now. But strangely, Earth wasn't completely frozen. The faint young sun paradox is one of the most interesting puzzles in planetary science. How did our planet keep liquid water and support life with such a weak solar furnace? The answer is an atmosphere that was a work of art in natural engineering, full of greenhouse gases that wrapped the planet in a warm, protective hug. Methane was in the air in amounts that would be poisonous to us, but it made the greenhouse effect so strong that it more than made up for how dim our star was when it was young. There were also levels of carbon dioxide in the air that were hundreds of times higher than they are now. We might think of these as pollutants now, but they were actually the Earth's heating system, a carefully balanced mix of gases that kept the oceans liquid and life going. The pressure in this old atmosphere was also different. It was probably 30 to 40% higher than what we feel now. If you could somehow survive the chemicals in the air, walking on this ancient Earth would have felt like being underwater at a shallow depth, with the air itself feeling heavy and dense. It would have been hard to breathe and hard to walk in that thicker air. Let's talk about those oceans, because they were probably the strangest thing about this ancient world. Picture yourself on what could be called a shoreline, even though the line between land and sea was much less clear than it is now. The water that touched your feet would have been a pale green or even orange colour. This was because iron and other minerals dissolved in it and formed big rusty clouds when oxygen was present. These weren't the clear blue waters that we think of when we think of unspoiled nature. Chemists today can barely make these soups in labs because they were so rich and full of minerals. The pH levels changed a lot compared to today, and the salinity was different too. Sometimes it was higher than today's oceans, and other times it was lower, but it always had a mix of dissolved metals that made the water taste bitter and metallic. The temperature of these old seas was another amazing thing. Water temperatures could change a lot if there weren't big continental masses and complicated ocean currents to keep them stable. Some areas may have been pleasantly warm, like a tropical lagoon today, while others may have been so hot that they could have cooked an egg. The thermal gradients made circulation patterns that we don't see today. These were like huge conveyor belts of mineral-rich water that moved nutrients and energy around the planet's surface. The chemistry of these ancient oceans was so rich and complicated that we need to rethink what we think water can hold in order to explain it well. The levels of dissolved iron were thousands of times higher than they are now in seawater. It was common for levels of hydrogen sulfide that would be dangerous today. The water itself was often too full of minerals, and they would come out of the water at the slightest change in chemicals. When storms stirred these old seas, they weren't just mixing water, they were doing huge chemistry experiments. The turbulence would mix different water masses, which would cause minerals to fall to the ground in large amounts and create underwater snowstorms of metal particles. The seafloor would have been covered in these chemical deposits, making landscapes of pure mineral beauty that we don't see on Earth today. But this is where the story gets really strange. These waters that looked like they were dangerous were full of life. Not the life we know. No fish, no seaweed, no colourful coral reefs, but tiny organisms that were so successful and creative that they were quietly shaping the future of the planet. These were cyanobacteria, which are often called blue-green algae, but they aren't algae at all. They were the first real innovators on Earth, and the first living things to figure out how to photosynthesize. Imagine billions and billions of these tiny engineers, each one smaller than the width of a human hair, floating in huge mats on the surface of the ocean. They took in sunlight and carbon dioxide during the day and let out oxygen as waste. It seems so easy and natural to us now, but this was a huge step forward in technology. It was like inventing fire, farming, and the internet all at once. It was hard to believe how big these groups of bacteria were. Single mats could stretch for hundreds of kilometers across shallow seas, making living carpets that could be seen from space. If there had been anyone in space to see them, they would have been able to see them. These weren't just random groups of microorganisms. They were very organized societies with complicated internal structures and advanced ways of communicating with each other chemically. Watching these bacterial mats move every day was like seeing the heartbeat of a planet. When the sun came up over the ancient oceans, photosynthesis would start happening all at once over millions of square kilometers. As the mat's metabolic machinery kicked into high gear, oxygen bubbles would start to rise through the water column. The mats themselves would also start to glow with a faint bioluminescence. As different types of bacteria reacted to the changing light, the color of the ocean surface would change slightly. These mats were some of the most productive ecosystems on Earth during the hottest hours of the day. They turned solar energy into biological energy with an efficiency that still impresses biotechnologists today. But their high productivity had effects that would change the whole world. The oxygen they made as waste was slowly but surely changing the chemistry of the oceans and the air. These mats of bacteria didn't just float around, they made amazing structures called stromatolites. If you could wade into those old shallow seas, you would see what looked like stone gardens under the water. Stromatolites were dome-shaped structures made up of layers of cyanobacteria. Each layer represented a season or year of slow bacterial growth. Some of these old monuments to microbial engineering grew to be several meters tall, making living rock forests under the water. Watching stromatolites form was like watching the slowest construction project in the world, but it was done with amazing accuracy. Every day, the bacteria would use photosynthesis to trap sediment and minerals around them. As they died, and new generations grew on top of their remains, layer upon layer built up, making these beautiful, otherworldly buildings. The patterns in these buildings were so regular that they were hypnotic. They were made up of concentric circles and undulating bands that reminded me of the rhythm of ancient days and seasons. The internal structure of these stromatolites shows us things about ancient life that seem almost too accurate to be true. Scientists can tell the difference between daily growth layers, seasonal changes, and even how plants and animals react to big storms or changes in the environment. Each stromatolite was like a geological library, keeping track of things like water chemistry, temperature, light levels, and biological activity with a level of detail that is hard to beat with modern scientific tools. Different types of cyanobacteria would make stromatolites with very different shapes. Some made tall, narrow columns that went up to the light. Some made wide, flat mounds that could cover a lot of the seafloor. Some of them made complex branching structures that looked like coral gardens underwater, even though the organisms that made them were much simpler than coral polyps. These bacterial groups fought hard and smart for light. Bacteria would make different pigments to absorb different wavelengths of sunlight. This would create rainbow-coloured mats where red, purple, green, and blue organisms arranged themselves in vertical layers based on how deep the light penetrated. This biological division of the light spectrum worked so well that very little solar energy went to waste. Even more amazing is that you can still see some of these buildings today. Living stromatolites still grow in places like Shark Bay in Western Australia, but they are now rare and interesting things instead of the most common type of life. They're like living fossils, direct links to that ancient world. They still follow the same biological blueprints that their ancestors perfected 3 billion years ago. But today's stromatolites are pale copies of their ancient cousins. The old versions were not only bigger and more common, but they also came in more shapes and grew in more interesting ways. Some ancient stromatolites show that they grew several centimeters a year, which is a very fast rate for structures made by tiny organisms. This rapid growth shows that the oceans of the past were much richer in nutrients and energy than today's seas, which are more stable and stratified. The land masses of this ancient Earth would have looked both familiar and completely new. There were continents, but they weren't the same ones we know today. The supercontinent of Ur was starting to take shape. It was a huge piece of land that would break up and come back together many times over the course of Earth's history. But these weren't the continents we know today, with their green forests. Under that strange sky, they were stark, rocky wastelands that went on forever. Erosion was always happening because there were no plants to hold the soil together. Rivers cut through rock with such ease that modern geologists would cry, and they carried huge amounts of sediment to the sea. Volcanism on a scale that dwarfs anything else in human history shaped the landscape. Huge shield volcanoes made mountain ranges that wind and water would later wear down to nothing. There were definitely some amazing eruptions, but the volcanic activity wasn't just about those. The planet was still cooling down from its violent formation and was still settling into the thermal equilibrium that would eventually make things more stable. One of the main ways that the planet got its warm gases was through volcanic outgassing. Every volcano was like a heating vent in a way, helping to keep the delicate balance that made life possible in the oceans. It's hard for us to understand how big ancient volcanism was. One volcanic eruption could release more material than all of the volcanic activity in recorded human history. Lava flows could cover areas the size of modern countries and build plateaus that are kilometers thick. These eruptions would have had an effect on the atmosphere all over the world, changing the climate and ocean chemistry for a short time. But the most interesting thing about these old landscapes may have been their colours. The exposed rock showed a range of minerals in their pure form, since there was no organic matter to make the rich browns and blacks of modern soil. The rocks that were rich in iron painted the landscape in red and orange hues that would have made Mars jealous. Other minerals added blues, purples and yellows, making a patchwork of colours that changed with the weather and the light. Because there were no plants, you could see every geological process, which is almost impossible to find on Earth today. You could read the history of the Earth in the rocks under your feet. Each layer and shape told stories of old seas, volcanic eruptions, and the slow, steady work of wind and water. These rock formations that were exposed made landscapes that were both beautiful and strange in shape. Wind erosion shaped soft sedimentary rocks into amazing shapes, while harder volcanic rocks stood as reminders of ancient disasters. Different types of rocks work together to make natural sculptures that are much bigger than any building made by people. Without soil or plants to absorb sound, these old landscapes would have had their own special sound properties. If someone were to visit, their footsteps would have echoed off the bare rock faces. Wind would have howled through stone formations in a way that is impossible in modern environments with plants. The sound of waves crashing against rocky shores would have echoed for kilometers across empty plains. When it rained, it was very different from the light showers we have now. Because the atmosphere was made up of different things, rain could be very acidic and dissolve rock at rates that would shock modern environmental scientists. These weren't the rains that keep our ecosystems alive. They were geological forces that changed the landscape with each storm. The high levels of sulfur dioxide and carbon dioxide in the air made ancient rain acidic. When these gases mixed with water vapor, they made solutions that could etch limestone, dissolve metal ores, and carve intricate patterns into rock surfaces that were already exposed. Some old rock formations still show signs of this acidic weathering, which is proof of weather conditions that are no longer present. These landscapes, which had no plants, were often hit by flash floods that caused a lot of damage. Storms could strip entire hillsides in a matter of hours if there were no roots to hold the soil in place or slow down the flow of water. Ancient rivers carried a lot of sediment, Some paleontologists think that erosion rates were 10 to 100 times higher than they are now in similar environments. But even in this harsh environment, life was still finding ways to settle down. The first organisms that lived on land were probably like the cyanobacteria that live in the oceans and make thin biological films on wet rock surfaces. These early life forms were very tough. They could live through huge changes in temperature, UV radiation that would kill most modern organisms, and chemical conditions that would be too much for even our strongest industrial bacteria. These early settlers of the land didn't just sit back and let their harsh environment change them. They actively worked to change it. Their biological processes started the slow process of making soil by breaking down rocks through both chemical and physical weathering. They made tiny oases with slightly better conditions that other organisms could live in. During this ancient time, the areas where land and sea met were especially interesting. Without clear lines made by plants, it was hard to tell the difference between land and water environments. During high tides, tidal zones could stretch for kilometers inland, forming huge wetlands that were not completely land or sea. These marginal environments were important for evolution because they were places where organisms could try out changes that would eventually let them fully colonize land environments. If you sign up for this channel, you'll hear more stories about how these early settlers on land led to the complicated ecosystems we see today. It's a journey that has lasted for hundreds of millions of years and is full of new ideas, deaths, and evolutionary leaps that seem almost too amazing to be true. We should take a closer look at the chemistry of this ancient atmosphere because it tells us a lot about how different this world really was. There was oxygen, the gas that keeps us alive, but not much of it. Most of it was stuck in rocks and minerals instead of being free in the air. Chemical reactions with iron and other elements quickly used up the small amount of free oxygen that was there. This might sound like a bad place to live, but for the creatures that lived in this ancient world, oxygen was actually bad for them. Most of the first living things were anaerobic, which means they could live in conditions that would kill us right away. They had developed complex biochemical systems to keep from coming into contact with oxygen, just like we would with cyanide gas. The biochemical machinery that these ancient organisms used to avoid oxygen toxicity was very advanced. They made special enzymes that could stop oxygen radicals from hurting cells before they could do so. Some organisms developed complicated compartmentalization systems that kept their sensitive biochemistry away from any oxygen that might be in their environment. It is almost poetic how ironic it is. Oxygen, the waste product of cyanobacterial photosynthesis, was slowly but surely changing the chemistry of the planet, making it unlivable for many of the organisms that had been on Earth for more than 1 billion years. The Great Oxidation event was one of the worst ecological disasters in Earth's history, but we might think of it as one of the best things that ever happened to our planet. The air always smelled like rotten eggs because hydrogen sulfide drifted through it. This was heaven for organisms that could break down sulfur compounds. They thrived in places where chemistry made energy for life, like hot springs and volcanic vents. Some of these old metabolic pathways are still around today in the most extreme places on Earth, like deep ocean trenches, volcanic hot springs, and the superheated depths of the Earth's crust. The sulfur cycle was much more active and complicated back then than it is now. Volcanic activity constantly put sulfur compounds into the air, and bacteria turn these compounds into energy through a series of chemical changes. The smell of hydrogen sulfide that would have filled the air wasn't just bad, it was the sign of a planet-wide energy economy based on sulfur chemistry. Methane was also very important for both chemical reactions in the atmosphere and biological processes. Methanogens, which are bacteria that made methane as a waste product of their metabolism, were some of the most successful organisms from this time. These organisms were so successful that they helped keep the planet warm by keeping the atmosphere rich in methane, even though the sun was dimmer. Because there was no ozone in the upper atmosphere, harmful ultraviolet radiation hit the surface of the Earth with such force that it would kill most modern life forms. This UV radiation was actually a big part of how the chemistry of the atmosphere worked, breaking molecules apart and putting them back together in new ways. The sky was a huge chemical reactor that got its energy from our young sun. Because there was no ozone in the atmosphere, The beautiful auroras we see from time to time would have been constant and much stronger. Charged particles from the solar wind could go much deeper into the atmosphere, making shimmering curtains of coloured light that could be seen even during the day. The whole sky would have been full of changing patterns of light, like a cosmic light show that went on all the time. But life wasn't just getting by in this very different world. It was coming up with new ideas at a speed that might seem impossible to people today. The genetic revolution that was going on in those old seas was making the building blocks for all living things on Earth, including us. These early microorganisms were working on the basic biochemical processes that still keep life going today, like photosynthesis, cellular respiration, DNA replication, and protein synthesis. Consider how big these new ideas are. Photosynthesis necessitated the development of highly intricate molecular machinery, adept at capturing photons and transmuting them into chemical energy. The organisms that learned how to do this didn't just make things easier for themselves. They changed the rules of life on Earth. For the first time, living things could use the sun's energy directly, instead of just using chemical energy from their surroundings. The photosynthetic machinery that developed during this time was so effective and well made that it has stayed mostly the same for 3 billion years. Plants, algae, and cyanobacteria that live today all use different versions of the same basic photosynthetic machinery that was developed in the ancient seas. This is one of evolution's most successful and long-lasting innovations. It is a biological technology that has never been fundamentally improved upon. The creation of DNA as a reliable way to store information was just as groundbreaking. RNA, or even simpler chemical systems, may have been used by earlier organisms to store genetic information. However, DNA was the first to provide information storage and replication that was both stable and accurate. This new idea made it possible for organisms to become more complex over time because reliable information storage made it possible for more advanced cellular machinery to be made. It's hard for people to understand how long these processes take. One stromatolite could be the result of thousands of years of slow bacterial growth. It took hundreds of millions of years for the Earth's atmosphere to change, from a greenhouse full of methane to one full of oxygen. By human standards, these changes didn't happen very quickly, but in geological terms, they were very quick. To put these timescales in context, think about how the whole history of human civilization, from the first farming settlements to now, is less than 1% of the time we're talking about tonight. The bacterial changes that happened 3 billion years ago had more time to grow and improve than all of human history put together 1,000 times. The weather on this old Earth was very different from what it is now. Weather patterns could change a lot in a short amount of time if there weren't any large land masses or complicated ocean currents to help. Changes in the atmosphere, volcanic activity, or the sun's output could cause ice ages to start and end more quickly. There is evidence that Earth may have gone through snowball events during this time, when ice covered the whole planet, even at the equator. These weren't slow coolings like the ice ages we know about from more recent geological history. They were quick, big changes that could change the surface of the Earth in thousands of years instead of millions. We still don't fully understand what caused these snowball events, but they probably had to do with feedback loops between the composition of the atmosphere, the circulation of the ocean, and the formation of ice. Once ice started to form at high latitudes, its ability to reflect light would have made things cooler, which could have led to runaway glaciation that could freeze the whole planet in a short amount of time. The recovery from these snowball periods was just as dramatic. Volcanic activity would continue as ice covered the land and sea, slowly raising the levels of carbon dioxide in the air. The planet would warm up quickly when the greenhouse effect finally became stronger than the ice's ability to cool by reflecting light. This would happen in a geologically short amount of time, changing the world from a frozen one to a greenhouse. These climate changes weren't just interesting geological events, they were evolutionary tests that made life change, come up with new ideas or die. Every crisis killed some organisms and gave others a chance to live. The organisms that survived these planetary upheavals were very tough. They had biochemical toolkits that worked in a wide range of temperatures, chemistries, and environments. When the climate got bad, These organisms learned how to survive by going into dormant states, reproducing quickly when things got better, and being very flexible in their metabolic pathways. Some organisms evolved the ability to switch between different types of metabolism based on the environment, while others evolved protective structures that could keep them safe from extreme temperatures or chemicals. This ancient Earth had a lot of minerals, which was amazing. Erosion happened at rates that concentrated valuable elements in ways we rarely see today because there were no plants to weather rocks slowly. During this time, huge amounts of iron, copper, gold, and other metals were deposited. Many of these metals are still being mined today. These weren't the scattered, weak ore bodies that are common in later geological periods. They were concentrated bonanzas of pure mineral wealth. The well-known banded iron formations in rocks from this time tell an interesting story about the chemistry of the ocean and early life. These formations are made up of layers of iron-rich and silica-rich rock that alternate. They were made when cyanobacteria made oxygen that caused dissolved iron in the oceans to fall out. Each band shows a cycle of photosynthesis and chemical precipitation, which makes a geological record of some of the first ecosystems on Earth. The creation of these iron deposits had a big effect on the chemistry of the ocean. The oceans slowly became less reducing and more oxidizing as free iron was taken out of the water. This change in chemicals killed off many of the anaerobic organisms that had thrived in iron-rich waters and made room for new organisms that could live in or even need oxygen. It's hard to understand how big these banded iron formations are. Some formations can be hundreds of meters thick and cover thousands of square kilometers. They are the result of iron falling out of oceans that had thousands of times more dissolved iron than today's seawater. These formations hold so much iron that they are one of the biggest iron reserves on Earth. They are the raw material for a lot of modern industry. The alternating bands in these formations give us very accurate information about the chemistry and biology of ancient oceans. Scientists can see changes in the seasons, longer-term climate cycles, and even individual biological blooms that are preserved in rocks. Each band is like a picture of how the ocean was at a certain point in Earth's long history. If you're still with me on this journey through deep time, you're experiencing something that not many people think about deeply. How strange our planet's past is. We often think of Earth as eternal and unchanging, but the world we've been exploring tonight was as different from modern Earth as an exoplanet orbiting a distant star. The most obvious difference is that there are no familiar life forms. There were no birds singing at dawn, no forests rustling in the wind, and no insects buzzing through the air. The sounds of this old world would have been mostly geological, waves crashing against rocky shores, volcanoes rumbling, and wind whistling through empty spaces. But this world looked empty, when in fact it was more alive than most places on Earth today at the microscopic level. The sounds of this ancient world would have been hauntingly beautiful in their strange simplicity. Without the complicated sound-absorbing structures that plants make, every sound would have travelled farther and clearer than it does now. Wind blowing through rock formations would have made natural music on a scale that is impossible to make today. Storms on this old Earth would have been amazing to see and hear. Hurricanes and typhoons could have been much stronger than anything we know about today if there were no plants to slow down the wind or spread out energy. Lightning strikes would have lit up landscapes that were all one colour of mineral, making it look like there was an electric rainbow world for a short time. Some of the most productive ecosystems ever were the bacterial mats that covered large parts of the ocean's surface. They changed solar energy into biological energy with a level of efficiency that still amazes biotechnologists today. These organisms were also very creative in their biochemistry, coming up with metabolic pathways that are so complex and elegant that they seem like they belong in science fiction. Some of these old bacteria could change the way they metabolized based on what they had to work with. They would photosynthesize when there was light. They could switch to chemical sources of energy in the dark or in shaded areas, breaking down sulfur compounds or other minerals. This metabolic flexibility let them live in almost every niche, from the sunlit surface waters to the dark depths of the ocean floor. By today's standards, these old ecosystems had a huge range of metabolic types. There could be dozens of different types of bacteria in a single bacterial mat, and each type is best suited for a slightly different type of chemical environment or energy source. The interactions between these different metabolic pathways made biogeochemical cycles that were very good at recycling nutrients and energy throughout the ecosystem. Some groups of bacteria learn to work together in very smart ways that make it look like they are smart. Different species would focus on different steps in complex chemical changes, making biological assembly lines that could break down or make compounds that no one organism could do on its own. These cooperative networks were the first steps toward the symbiotic relationships that would lead to complex cells and eventually multicellular life. The genetic changes that happened during this time set the stage for all future life on Earth. DNA became a stable, replicable way to store information, which let organisms grow and get more complicated over time. The evolution of cellular organelles, specialized structures within cells, enabled the development of more sophisticated biochemistry and eventually gave rise to the first eukaryotic cells, the ancestors of all plants, animals, and fungi. The change from simple prokaryotic cells to more complex eukaryotic cells was one of the most important changes in evolution in the history of Earth. This change needed the creation of internal membranes that could separate different cellular functions, which made biochemistry much more complex and cells much more complex. But maybe the most interesting thing about this ancient world was that it was a place where planets were built. The cyanobacteria weren't just living in their environment, they were changing it by changing the chemistry of the oceans and atmosphere through their metabolic processes. This was the first time that life was seen as a geological force that could change the chemical and physical properties of a whole planet. The idea that life is a geological force is still changing the way we think about how planets change over time. The acknowledgement that living organisms can fundamentally transform planetary chemistry, climate, and even geology has significant ramifications for our comprehension of Earth's history and our ability to identify signs of life on other celestial bodies. The oxygen they released as waste gradually built up in the air, making it possible for more complex forms of life to grow. But this wasn't a straight line of progress. The rising levels of oxygen also caused one of the worst extinction events in Earth's history, killing off many of the anaerobic organisms that had ruled the planet for billions of years. The Great Oxidation Event was both the end of something and the start of something new. It was the end of the first great age of life on Earth, the age of anaerobic microorganisms, and it set the stage for everything that came after. Over time, the oxygen-rich atmosphere would support bigger, more complex organisms that could use aerobic respiration to make energy in ways that had never been done before. It didn't happen all at once or in a straight line when the world went from anaerobic to aerobic. It took hundreds of millions of years, and the amount of oxygen in the air changed a lot as different biological and geological processes fought for control. Oxygen levels may have been higher than they are now at some times, and lower than they are now at others. This would have made it hard for aerobic organisms that were used to living at those levels. The geological processes that shaped this ancient Earth were on a scale that is hard for humans to imagine. Many times mountain ranges grew and then were worn away. The planet's crust moved and changed shape, which opened and closed ocean basins. Volcanic activity created huge plateaus of igneous rock that would later serve as the base for continents. The tectonic processes that were going on at this time were very different from the ones that are going on now. The Earth's crust was thinner and more flexible, which made it easier for the continents to change shape quickly and dramatically. It was possible to put together and take apart whole continents in timescales that seem impossibly short by today's standards. During this time, the magnetic field that protects Earth from harmful solar radiation was probably weaker and more variable. This meant that charged particles from the sun could directly interact with the upper atmosphere, making auroras that were much more beautiful than what we see now. During times of high solar activity, the whole sky might have been filled with moving curtains of coloured light. The changes in Earth's magnetic field during this time had a big effect on how life evolved. When magnetic protection was weak, organisms on the surface would have been exposed to more cosmic radiation. This could have led to more mutations and changes in evolution. Some scientists think that These times of magnetic instability may have sped up the rate of evolutionary change. These interactions between solar particles and the atmosphere also played a role in the complicated chemistry that happens in the air's upper layers. High-energy reactions made and broke molecules at a rate that would always change the makeup of the atmosphere. This chemical activity caused the climate to change a lot during this time in Earth's history. Rivers in this ancient time were very different from the ones we know today. They carried huge amounts of sediment because there were no plants to slow down the water and stop erosion. Some ancient river systems moved more sediment in one flood than modern rivers do in decades. These sediment loads made huge deltas and alluvial fans that could bury whole landscapes under layers of rock and mineral debris. Ancient river systems looked very different from rivers today. Without plants to hold the banks in place, ancient rivers were probably much wider and shallower than modern ones. Their channels would move all the time, and during a single flood, they could move across the entire valley floor. The braided patterns that these channels would have made landscapes with amazing geometric complexity. Because there wasn't soil like we know it now, weathering and erosion worked differently. Chemical weathering, which is the breaking down of rock by chemical reactions, was often more important than physical erosion, which is what happens in most modern environments. The acidic air and rain could break down even tough minerals, making landscapes that were shaped by both chemical and mechanical forces. But even in this harsh and strange world, the building blocks of our modern biosphere were being put in place. Organisms that lived in these ancient environments came up with every major biochemical process that keeps life going today, such as photosynthesis, DNA replication, and cellular respiration. During this time, the genetic code that controls all life on Earth was standardized. This made the universal biochemical language that links all living things, from bacteria to blue whales. The fact that the genetic code is the same for all living things on Earth is one of the strongest pieces of evidence for their common ancestry. The fact that every living thing, from the simplest bacterium to the most complex plant or animal, uses the same basic system to turn genetic information into proteins suggests that this system was perfected very early in Earth's history and has never needed to be changed. The range of metabolic strategies that were created during this time was amazing. Some organisms learned how to get energy from iron, while others learned how to get energy from sulfur compounds or hydrogen gas. This biochemical research led to the development of a set of metabolic processes that life still uses today, especially in extreme environments where normal photosynthesis and respiration aren't possible. The metabolic advances of this time weren't just interesting, they were major breakthroughs that changed the limits of what kinds of environments could support life. Every new metabolic pathway was like a key that opened up new ecological niches, letting life move into places that were once too harsh for it to survive. This eventually made the biosphere bigger to include almost every type of habitat on Earth. Even though these ancient ecosystems were very small, their physical structure was very advanced. Bacterial mats were not just random groups of microorganisms. They were very organized communities with different jobs, ways to talk to each other chemically, and ways to work together that made them act like superorganisms. Different kinds of bacteria would stack themselves in vertical layers inside these mats, with each one living in the area where its specific metabolic needs could be best met. Photosynthetic organisms would thrive in the upper layers where there was light, while chemosynthetic organisms would thrive in the deeper, darker areas where they could get energy from different chemical sources. The way these layers were put together made ecosystems that were very stable and could last for thousands of years with little change. The chemical gradients in these mats were so strong that they made microenvironments that were as different from each other as continents, all in structures that were only a few millimeters thick. When you think about how modern ecosystems are always changing, it's amazing how stable these ancient bacterial ecosystems are. Modern ecological communities are always changing because of competition, predation, and changes in the environment. However, these ancient bacterial mats could keep the same structure and function for millions of years. The organisms involved had evolved to take advantage of very specific chemical niches, which made this stability possible. This created a biological economy where specialization reduced competition. The seasons on this old Earth would have been very different from what we know today. Some areas might have more extreme seasonal changes than others, and some might not have any at all because there aren't any big continental land masses to moderate the climate. The planet still tilted on its axis and orbited the Sun in an ellipse just like it does now. However, the way the climate reacted to these changes was very different because the atmosphere and oceans were very different. Some areas may have had temperature changes of 50 degrees or more between summer and winter, while others stayed about the same all year. The way rain, evaporation, and airflow worked together would have made seasonal rhythms that are very different from what we see in modern meteorology. The growth patterns of stromatolites and other geological formations show how these seasonal cycles change. Scientists can learn not only what the climate was like, but also how it changed over days, seasons, and longer cycles by looking at these old records. It's like reading a stone diary that tells the story of a planet that is no longer there. It is truly amazing how well these old seasonal records have been kept. Some stromatolites have daily growth layers that are so regular and well defined that scientists can count them like tree rings. This lets them figure out not only seasonal patterns, but also the length of ancient days and years. 3 billion years ago, the Earth spun faster, so days were only about 18 hours long. The Moon was also closer, which made tides much more dramatic than they are now. These stronger tidal cycles had a big impact on how life spread and changed over time. Stromatolites thrived in intertidal zones, which had much more dramatic changes in water level. This made it possible for organisms that could survive being submerged and exposed to thrive. The tidal mixing also helped spread oxygen and nutrients throughout shallow marine environments, which helped the complex bacterial ecosystems that were changing the planet. Because the Moon was closer, its pull on Earth's geology was stronger. Tidal forces would have made volcanoes erupt more often and the crust move around more. Some scientists think that these stronger tidal forces may have had something to do with the fast geological changes that happened during this time in Earth's history. The dance between Earth and its moon was one of many things in space that affected the weather on our planet long ago. The solar system was younger and more chaotic, with asteroid impacts happening much more often than they do now. These impacts weren't just destructive forces, they were also ways to bring water, organic compounds, and important elements from the outer parts of the solar system to the surface of the Earth. During this time, some of the biggest impact events may have temporarily sterilized large areas of the planet's surface. However, life was able to recover and recolonize these devastated areas fairly quickly because it is so adaptable and resilient. After each major impact, there were times of rapid evolutionary change as organisms adjusted to the new conditions and filled new ecological niches. The record of impact craters from this time shows that the planet was always being hit by things from space. Most of these old craters have been erased by later geological activity, but they had a big impact on how Earth evolved in the past. The heat from big impacts could have caused changes in the global climate, and the mixing of materials on the surface and below the surface could have made new chemical environments for life to explore. As we explore the microscopic world that ruled this ancient Earth, we find organisms that are more complex than we thought simple life could be. The cyanobacteria that lived in these ancient seas weren't just simple photosynthetic machines. They were complex biological systems with internal structures and control systems that were as good as those of modern organisms. These old bacteria had already changed many of the parts of cells that we think of as being more advanced. They had advanced membrane systems that could control the movement of materials in and out of the cell. They had made complicated machines for making proteins that could make hundreds of different kinds of proteins. Most impressively, they had developed complex ways to fix DNA damage, which let them keep their genetic integrity even in the harsh radiation environment of ancient Earth. The photosynthetic machinery of these ancient cyanobacteria was an amazing feat of molecular engineering. Hundreds of different proteins had to work together in very precise geometric patterns to capture light energy and turn it into chemical energy. These patterns were able to channel energy very efficiently. For 3 billion years, this biological machine has worked without any major changes. But photosynthesis was only one of many new ways that living things were using energy during this time. Other living things were also making very advanced systems for getting energy from chemical reactions. Bacteria that reduced sulfur evolved complex electron transport chains that could get energy from sulfur compounds with an efficiency that modern industrial chemists find hard to match. Methanogenic bacteria made biochemical pathways that turned simple organic compounds into methane. This added to the greenhouse gases that kept the planet warm. These organisms were so successful that the methane they excreted became one of the most common gases in the atmosphere, changing the planet's climate system in a big way. The variety of these metabolic pathways shows something deep about what life is. Life was not limited to a single energy source. It demonstrated the ability to utilize nearly any chemical reaction that produced usable energy. This ability to adapt to different environments would be very important as the Earth's environment changed over millions of years. The social behaviors of these ancient bacterial communities were much more complicated than we would expect from such simple organisms. A lot of species came up with advanced chemical communication systems that let them work together over long distances. When the environment changed, bacterial communities could spread information about the changes faster than the changes themselves. Some groups of bacteria came up with what can only be called primitive farming. Some species would grow other bacteria that made useful chemicals, turning them into biological factories that could make complex chemicals faster than any one organism could do it alone. These early instances of biological cooperation foreshadowed the symbiotic relationships that subsequently led to the emergence of complex cells and multicellular organisms. The systems these old ecosystems came up with for dealing with waste were very advanced. One species' toxic waste became another species' necessary nutrients, making closed-loop systems that reduced waste and made the most of resources. These old examples of biological recycling were so good that they made modern industrial processes look bad. Different groups of bacteria competed with each other, which led to quick improvements in both offensive and defensive biochemical strategies. Some organisms created chemical weapons that could kill other organisms, while others evolved ways to fight back against these biological toxins. This ancient arms race between different types of life led to the development of more and more complex biochemical systems. During this time, genetic transfer mechanisms developed that were very important for spreading new ideas throughout the global bacterial community. Many ancient bacteria could get new genetic abilities directly from other organisms through horizontal gene transfer, which is different from how modern organisms mostly get genetic material from their parents. This made it possible for successful new ideas to quickly spread through whole groups of people, speeding up the rate of evolutionary change. Some ancient bacteria have magnetic properties that are worth studying because they show that complex navigation systems existed long before any animals did. Some cyanobacteria had tiny magnetic particles inside them that helped them figure out where they were in relation to Earth's magnetic field. This biological compass system helped them stay in the best position for photosynthesis and find their way through the water column's complicated three-dimensional spaces. These magnetic navigation systems were so finely tuned that they could pick up changes in the strength of the magnetic field that modern scientific tools would have a hard time picking up. The biological processes that let these bacteria make and organize magnetic particles in their cells were very advanced and involved complicated biochemical pathways that scientists still don't fully understand. The evolutionary pressure to create these navigation systems shows how complicated ancient marine environments were. The ancient oceans were not simple, uniform places. They had complicated gradients of light, temperature, chemistry, and nutrients that organisms had to carefully navigate in order to survive and thrive. As we look at these old seas tonight, where are you listening from? The iron atoms in your blood may have once been part of the magnetic navigation systems that ancient bacteria used. They have been recycled through billions of years of planetary history. Viruses played a part in these old ecosystems, which makes it even harder to understand how life began. Viruses were already around 3 billion years ago. They infected bacteria and helped new genetic changes happen by moving genetic material between different organisms. These old viral infections weren't just sources of disease, they were also engines of evolutionary change that sped up the development of new biological abilities. It was hard for ancient bacteria and their viruses to get along. Viral infections could kill individual bacteria, but they also made it possible for bacteria to exchange genetic material, which helped bacterial populations adapt more quickly to changes in their environment. This old dance between hosts and parasites set up ways for living things to interact that still affect evolution today. Some scientists think that viruses may have been very important in the evolution of DNA as the main genetic material for life. The need to protect genetic information from viral attacks may have led to the development of more advanced DNA repair systems, which eventually led to the stable genetic systems that are found in modern life. There were more than just bacteria and viruses in the oceans of the past. There were also more complex organic structures that were at the edge of living and non-living things. These early life forms may have been important steps in the evolution of cellular life, giving scientists a way to try out different ways of organizing living things. Some of these old organic structures were like biological labs where scientists could try out and improve different chemical reactions. The reactions that worked best would be used in living things, and the ones that didn't work would be thrown away. This trial and error method of coming up with new biochemical ideas was very wasteful by today's standards, but it worked very well to come up with new biological ways to solve environmental problems. The fossil record from this time not only has the remains of organisms, but it also has chemical traces of their metabolic activities. These molecular fossils, also known as biomarkers, give us a lot of information about ancient ecosystems that we couldn't get from regular fossils alone. By looking at the kinds and amounts of different organic compounds in old rocks, scientists can figure out how living things used to work in the past. Some of these molecular fossils are so well preserved that they still have information about how ecosystems changed with the seasons in the past. Scientists can find out not only what kinds of organisms were there, but also when they were most active, what they ate, and how their numbers changed over time. You can look at detailed ecological surveys of ecosystems that existed billions of years ago. To keep these molecular fossils, very specific conditions had to be met. This tells us something important about the environments of the past. To keep these chemical signatures from breaking down, organic matter had to be buried quickly in sediments that didn't have any oxygen in them. This suggests that ancient marine environments had places where sedimentation happened quickly and oxygen levels dropped, which helped preserve fossils very well. Isotopic analysis of preserved organic compounds shows how chemically complex these old ecosystems were. Different metabolic processes leave behind unique isotopic signatures that can be found billions of years later. Scientists can use these chemical fingerprints to figure out not only what organisms were there, but also how they were living in their old environments. For instance, sulfur isotope ratios can show if ancient bacteria were using sulfur-based metabolism, and carbon isotope patterns can show if different types of photosynthesis were happening. Nitrogen isotope signatures can tell us about how nutrients move around and how available different nitrogen compounds are. Each part of the story about how these old ecosystems worked is told by a different part. The worldwide spread of these isotopic signatures shows that many of the basic biogeochemical cycles that happen on Earth today were already in place 3 billion years ago. The cycling of carbon, nitrogen, sulfur, and other elements through the biosphere was already a planetary-scale process driven by the metabolic activities of ancient microorganisms. As we get closer to the end of our journey through this ancient world, it's a good time to think about what we've learned about our modern Earth. The planet we live on seems stable and good for life, but it has actually changed slowly over billions of years, with big changes that changed everything from the chemistry of the oceans to the makeup of the atmosphere. 3 billion years ago, the organisms that lived were not just simple ancestors of modern life. They were advanced biochemical engineers whose work made all later life possible. The air we breathe, the soil that grows our food, and the mineral deposits that power our technology are all gifts from those ancient microbial communities. Knowing about this long history also helps us understand the changes that are happening to the environment right now. Earth has gone through some very big changes in the past, some of which were much worse than what people are doing now. But life has not only survived these changes, it has often become stronger and more diverse than it was before. This doesn't make taking care of the environment any less important today, but it does remind us that our planet is stronger and more adaptable than we sometimes think. Biological innovation, chemical cycling, and planetary feedback systems are still at work today, just in different ways because of the complex ecosystems that have developed over geological time. The story of Earth 3 billion years ago is really a story about change and what could happen. Life not only survived, but thrived in conditions that seemed impossibly harsh and alien. It did this by coming up with new ways to live and adapt, which eventually led to the rich, complex biosphere we know today. Every tree, animal, and breath of air that is rich in oxygen is proof that those ancient microbes were successful. This ancient world has left a legacy that goes far beyond the biological world. The chemical reactions that happened in the oceans and atmospheres of the past set up the geochemical cycles that still control the chemistry and climate of Earth today. The mineral deposits that formed during this time are what most of today's technology is made of. The iron precipitation processes that happened in ancient seas may have even changed the magnetic field that protects us from harmful cosmic radiation. It is very important for technology to understand these old biological systems. Modern biotechnology is increasingly looking to ancient organisms and metabolic pathways for ideas on how to make new industrial processes. Extremophile bacteria that live in places that are like those that existed 3 billion years ago are helping us understand how biological systems can work in ways that would destroy normal technology. Some of the most exciting new ideas in renewable energy technology are based on biological processes that were perfected billions of years ago. The photosynthetic machinery that evolved in ancient cyanobacteria is the basis for artificial photosynthesis systems that could provide clean, renewable energy. Biological fuel cells that could power anything from spacecraft to medical devices are based on the electron transport systems that ancient bacteria used to get energy from their surroundings. Our understanding of Earth's ancient biosphere also has a big impact on the search for life on other planets. The types of places that could have supported life on early Earth, high radiation, extreme chemistry, and changing temperatures are like the kinds of places that could exist on Mars, Europa, or other worlds in our solar system, and beyond, that might be able to support life. We can better understand what signs of life might look like elsewhere in the universe by learning how life worked on Earth under these conditions. The atmospheric signatures that ancient life on Earth left behind can be used to find signs of life on other planets. The oxygen and methane that ancient ecosystems made mix together in ways that are thermodynamically unstable without life. Similar atmospheric imbalances on faraway planets could mean that biological processes like those that happened on Earth long ago are still happening. As you fall asleep tonight, you might dream of those old seas, full of life that you can't see, under skies painted in colours that don't exist anymore. You could picture walking on shores made of pure mineral crystal, breathing air full of greenhouse gases, and seeing stromatolites grow in real time under the light of our younger, dimmer sun. These dreams aren't just flights of fancy, they're links to our deepest roots, reminders that we are all children of that ancient world, carriers of genetic information and biochemical processes that have been perfected over 3 billion years of planetary evolution. In a very real way, those ancient cyanobacteria are still alive in us, in the cells that make every breath, heartbeat, and thought happen. The mitochondria in our cells are the descendants of bacteria that learned how to use oxygen to make energy. The chloroplasts that let plants photosynthesize are related to the cyanobacteria that first learned how to use sunlight. Even the ways that our DNA repairs itself can be traced back to the molecular systems that ancient organisms used to deal with the harsh radiation environment of early Earth. 3 billion years ago, the Earth may have seemed like a strange place, but it was where the basic processes of life were made. Knowing about this old part of our planet's story doesn't just satisfy our scientific curiosity, it also connects us to the deep time that shapes everything we see around us, from the rocks under our feet to the stars above our heads. The atoms that make up your body have been a part of this planet's story since the beginning. The carbon in your cells may have come from carbon dioxide in the air a long time ago. The iron in your blood may have come from old oceans that were full of dissolved metals. The oxygen you breathe is the result of billions of years of photosynthesis that started in those old bacterial mats. This atomic recycling links you to the history of life on Earth and to the cosmic processes that made the elements themselves. The nuclear furnaces of ancient stars made the heavier elements in your body, and supernova explosions spread them throughout the galaxy. The hydrogen in your body is as old as the Big Bang. You are literally made of star stuff that has been put together over billions of years of planetary evolution. The story we've talked about tonight is only one part of the much bigger story of how the universe has changed over time. The same physical and chemical processes that formed Earth 3 billion years ago are still going on in the universe, and they could create life in places we can't even imagine. Our ancient Earth is a model for how these things work, and a reminder of how creative and strong life is. The future evolution of our planet will undoubtedly bring changes as dramatic as those we have explored tonight. In the long run, the sun will get brighter, the continents will move, and life will change and adapt to new situations. In a few billion years, Earth might become an alien world again, changed by things we can only barely picture. But the basic rules that governed life 3 billion years ago, being able to get energy from the environment, reproduce and evolve and adapt to changing conditions, will still be in place, no matter what forms life takes in the future. As our planet moves through deep time, the creativity and strength that helped life thrive in what seemed like hostile conditions on ancient Earth will continue to find new ways to show themselves. Good night, time travelers. When you sleep, you're part of the same cycles of energy and matter that have kept life going on this amazing planet for billions of years. This connects you to all living things today and to the ancient world that made all life possible. Your story is also the story of Earth 3 billion years ago, written in the atoms of your body and the biochemical processes that keep you alive. You have the legacy of 3 billion years of evolutionary change inside you. You also have the wisdom of many generations of organisms that learned how to survive in a world that was always changing. You are the most recent chapter in a story that started in those ancient seas and will continue long after our current forms of life have died out and new forms of creative power have appeared on Earth. Take a moment to close your eyes and picture yourself at the end of the world. The wind carries whispers of ice crystals across a never-ending white space, and the thickest sheet of ice on Earth is under your feet. Antarctica is a continent so far away and unwelcoming that people didn't know it existed until just 200 years ago. But tonight, as you get comfortable, we're going to talk about one of the most interesting questions ever asked about this frozen world. What if a secret civilization has been living under all that ice for thousands of years? Before you write this off as just a story, think about this. Antarctica has more secrets than maybe any other place on Earth. It's a continent that's bigger than the US and Mexico put together and is covered in ice that is up to 3 miles thick in some places. We know more about the surface of Mars than we do about the bedrock under the Antarctic ice. Even though we can see the farthest parts of space and read the human genome, Antarctica still won't tell us what's under its frozen surface. People have always thought about the idea of hidden civilizations. We've always been interested in the idea that there are societies that have developed in ways that are completely different from ours, like Plato's Atlantis or the mythical Shambhala. But Antarctica is a great place to make such guesses because it's so hard to see. We only found these subglacial lakes in the last few decades, and they have changed the way we think about what can happen in such harsh environments. Lake Vostok, the biggest of these hidden bodies of water, has been sealed off by ice for millions of years. It has more water than Lake Ontario and has been cut off from the rest of the world since before our ancestors learned to walk on 2 legs. Scientists finally got to the bottom of this ancient water and took a sample. What they found was amazing. Life, not complex life, but microorganisms that evolved in complete isolation and developed traits that are not found anywhere else on Earth. People think that, if life could survive in such harsh conditions, what else might be possible down there? The geological history of Antarctica makes the mystery even deeper. This continent wasn't always the frozen desert it is now. It was much closer to the equator millions of years ago, and it was full of life and lush forests. Fossils found in rocks in Antarctica tell us about a time when dinosaurs lived in warm, humid forests that are now covered in ice. There are coal deposits buried under the ice that were made from plants that lived a long time ago. This shows that Antarctica used to have a temperate climate. But this is where our story gets interesting. What if Antarctica didn't change into an icy continent as slowly as we think it did? What if there were societies that learned to adapt, live underground, and make use of the special features of their changing world? To figure out how a secret civilization could live in Antarctica, we need to look at how life has learned to thrive in very harsh conditions on the surface world. In the deepest parts of our oceans, around volcanic vents where the temperature can reach hundreds of degrees, whole ecosystems thrive without ever seeing the sun. Chemosynthesis, not photosynthesis, is what powers these communities. They get their food from chemical reactions that involve sulfur and other minerals. Could the same ideas work under the ice in Antarctica? There is a lot of geothermal activity under the continent. Under the ice, volcanic systems make warm spots that could, in theory, support complex ecosystems. Geothermal energy can heat whole cities, as we can see in Iceland. Even in the middle of winter, hot springs in Yellowstone make oases of life. Why not under the ice in Antarctica? Picture a civilization that found these geothermal sources thousands of years ago. Maybe during the last ice age, when Antarctica was easier to get to and the sea levels were lower. Instead of running away as the ice sheet got thicker, they changed. They learned how to use the Earth's internal heat to grow crops in underground chambers warmed by volcanic springs. They built a society that was completely separate from the surface world. This imagined civilization would have grown in very different ways than ours. Their society might have had very different priorities if they didn't have to compete for land and didn't have to worry about weather-related disasters all the time. They may have become experts in sustainable living out of necessity, learning to recycle everything and live in perfect harmony with their closed ecosystem. The technology they made would be very different from what we know. They may have learned how to work with ice instead of metals mined from the surface. They could have made tools and buildings out of this plentiful resource. They might have found ways to clean and change ice that we can't even imagine, and they might have even learned how to change its molecular structure to make materials with properties we don't understand. They probably had an amazing understanding of sound. Sound travels differently through ice than through air. A civilization that lived only in this kind of environment would have come up with very advanced ways to use sound for communication, navigation, and maybe even building. They might be able to talk to each other over long distances by using ice's special sound properties. Think about how they feel about the dark. These imagined people who live in Antarctica would have learned how to live in constant darkness, unlike surface civilizations that plan their lives around the cycle of day and night. Their senses would have changed in ways that seem almost magical to us. They could have made art and music that no one else has, and they could have made beauty in ways that people who live on the surface couldn't even understand. It would be interesting to think about how the social structures of such a civilization would work. If surface societies weren't so far apart and had so many natural barriers, they might have come up with different ways to run their governments and organize their societies. In their harsh environment, working together would be necessary for survival. This could lead to social systems that put the needs of the group above those of the individual, which would be strange to our more individualistic surface cultures. But let's stop for a moment and look at the proof. The thought of a hidden civilization in Antarctica is interesting, but what would we really expect to see if such a society did exist? This is where our bedtime story meets real scientific research, and the results are interestingly unclear. First, there would be heat signatures. Even a civilization that used geothermal energy on a large scale would make heat patterns that satellites could see. Different space agencies keep an eye on Antarctica all the time, and they have found many thermal anomalies. Most of these are thought to be caused by known geological features like volcanic vents and geothermal fields. But this monitoring might not be able to find a civilization that is very well hidden. If a society like that had thousands of years to get better at hiding things, they probably would have figured out how to reduce their thermal footprint, maybe by sending extra heat deep underground or spreading it out in ways that look like natural geological processes. Second, we might expect to see strange seismic activity. Even a technological civilization that has learned to live underground would probably make vibrations and sounds that are different from those found in nature. Antarctica does have strange seismic events that don't always fit with what we know about geology, which is interesting. Some of these strange things happen in ways that scientists don't fully understand. The issue of resources is also at hand. For a civilization to survive, it needs materials to build with, food to eat, and energy to power its activities. Antarctica has hidden valleys and mountain ranges that are full of minerals that could, in theory, support a technologically advanced society. If a civilization learned how to use the geothermal energy sources we talked about, they could get almost unlimited power from them. Food production is harder, but not impossible. In theory, hydroponic and chemosynthetic food production could keep a group of people alive in underground chambers. Deep-sea volcanic vents are home to some of the most productive ecosystems on Earth. They support complex food webs without any help from photosynthesis on the surface. The same ideas might work for communities that live underground in Antarctica. No matter where you are in the world right now, think about how different your relationship with the environment would be if your ancestors had chosen to live underground instead of constantly changing the surface world to meet their needs. The mental effects of this kind of civilization would be huge. How would human consciousness evolve in a realm devoid of horizons, absent the expansive sky that has significantly influenced our terrestrial psychology? Would they have the same urges to explore and grow that have been a part of human history? Or would their closed-off world lead to different kinds of intellectual and spiritual growth? Maybe they would have become experts at exploring their own minds, creating types of consciousness and awareness that we can hardly picture. If the weather, seasons, and surface environments hadn't changed all the time, they might have turned inward and developed deep traditions of meditation, mental discipline, and psychological understanding that are much deeper than ours. Their relationship with time may also be fundamentally different. People who live on the surface plan their lives around the cycles of the sun, the seasons, and the way celestial events move across the sky. An underground civilization would have to make time systems that are very different from ours. They may have devised methods for measuring time predicated on geological processes, thermal cycles, or other phenomena that function on scales significantly distinct from our conventional days, months, and years. The art and culture of a society like this would be completely different from anything else. They would have developed their own tastes in art, based on different things, if they hadn't been able to see landscapes, sunsets, and the natural world, which have inspired so much human creativity. Maybe they learned how to make beautiful things out of ice and stone, making sculptures and buildings that turn natural caves and underground spaces into works of art. Their music might use the natural acoustics of ice caves to make songs that sound magical to people on the surface by using reverberation and resonance in new ways. They might have instruments that are unique to them and are made to work with the specific sounds of their underground space. In a civilization like this, literature and storytelling would probably deal with very different topics than they do now. Instead of tales of conquering distant lands or crossing oceans, their stories might look into the depths of the mind, the mysteries of geological time, or the subtle links between temperature, pressure, and the change of matter. Now let's look at some of the more interesting pieces of circumstantial evidence that make people wonder about the mysteries of Antarctica. Over time, different explorers and scientists have talked about strange things happening in Antarctica that don't fit with what we already know. Admiral Richard Byrd, a well-known polar explorer, wrote in his diary about finding a warm, green valley during his 1947 expedition. He said it was home to an advanced civilization. Most historians don't believe these stories because they think they are either made up or based on natural events that have been misinterpreted. However, they continue to capture the public's imagination because Antarctica is still mostly unexplored. In more recent times, satellite images have shown strange geometric patterns under the ice in some areas. Glaciologists say that most of these are natural formations made by the flow of ice and the shape of the land below. However, some patterns are still hard to put into a clear category. Because of the low resolution of current satellite technology, many details are still unclear. There are also some strange things about international Antarctic policy. The Antarctic Treaty, which was signed in 1959, says that Antarctica is a scientific preserve and forbids military activity on the continent. This treaty is good for science and the environment in many ways, but some people say it also stops people from doing a lot of exploration that could find hidden features under the ice. Different countries still have territorial claims on the continent, but these claims are put on hold by the treaty. It's interesting to note that these territorial boundaries often seem to focus on areas where unusual geological or thermal features have been found. However, this could just be because people naturally want to claim areas that might be useful for science or business. There are also stories from scientists who have spent a lot of time in Antarctica, which is probably the most interesting thing. There is a lot of research on how being alone for a long time in such an extreme environment affects the mind. However, some researchers have reported experiences that don't fit into the usual categories of hallucinations or stress caused by being alone. Many of these stories talk about feeling like someone is watching them, hearing sounds that don't match up with known wind or ice phenomena, and sometimes seeing structures or lights that shouldn't be there in the Antarctic landscape. Most of these experiences can be explained by the well-known effects of extreme isolation on how people see things, but they add to the feeling that Antarctica has secrets that we haven't found yet. Let's think about what it would be like if our surface civilization and a secret society in Antarctica ever met. In this case, we need to think about how different two branches of human civilization would have become after thousands of years of separate evolution. It would be interesting just to see the difference in technology. We learned about metallurgy, electronics, and mechanical engineering, but they may have learned about different areas of chemistry and physics. In some ways, they may know a lot more about crystalline structures, thermodynamics, and pressure systems than we do, but they may not know anything about technologies we take for granted. Communication would be a fun challenge. When people are cut off from each other, language changes quickly. After thousands of years of separate development, communication systems would probably look very different from any surface language. But math and some basic scientific ideas would help people understand each other better. The cultural exchange would be very deep. They would have ideas about human society, philosophy, and the connection between consciousness and the environment that could change the way we think about what it means to be human. At the same time, our stories about how agriculture, cities, and global communication networks have changed the world would be just as revolutionary to them. They would have learned to live within the strict limits of their closed ecosystem, which would have forced them to develop sustainable living practices. Their understanding of resource cycling, energy efficiency, and ecological balance could offer essential insights for our surface civilization as we confront environmental challenges. As we go deeper into this journey of thought tonight, let's think about why the idea of hidden civilizations still fascinates us. Maybe it's because these kinds of things make us remember that the real world is much stranger and more amazing than we think it is. Life has existed on Earth for billions of years, and human civilization is just a small part of that long history. There are many mysteries in the Earth below our feet. We have only explored a small part of our oceans, mapped a small part of the cave systems that run through the continents, and barely begun to understand the complicated ecosystems that exist in very harsh places. If life can thrive around superheated volcanic vents on the ocean floor, if microorganisms can survive in solid rock miles beneath the surface, and if entire forests can exist in caves that never see sunlight, then maybe the idea of a hidden human civilization isn't as crazy as it sounds. The scientific method tells us to make decisions based on evidence, and right now, there is no solid proof that there are hidden civilizations on Earth. But science also teaches us to keep our minds open to new ideas, to keep questioning what we think we know, and to remember that the universe is always stranger and more amazing than our theories say it is. Antarctica is the biggest unexplored area left on Earth. There are mountain ranges, valleys, and ecosystems that we've never seen or studied under the ice. The continent has ice cores that keep records of the atmosphere from hundreds of thousands of years ago. These cores give us a detailed picture of the history of Earth's climate. It has meteorites from Mars and other planets that can help us learn more about the solar system as a whole. And it has those strange subglacial lakes, which are ecosystems that are cut off from the rest of the Earth's biosphere and may have forms of life that evolved on their own. In a place like this, where there are so many mysteries and extremes, it's natural for the mind to wander to ideas that go beyond what we already know. The question of whether or not a hidden civilization really exists under the ice in Antarctica is important because it reminds us to stay curious about the unknown and to remember that reality is often bigger than what we know. The story of Antarctica is really about how Earth can surprise us. Scientists didn't think it was possible for life to exist on this continent, but it has shown them forms of life that they didn't think were possible. It has also shown them geological processes that went against established theories and climate records that changed how we think planetary systems work. It seems like every new thing we find in Antarctica opens up more possibilities for what could be out there in the harshest places on Earth. As you fall asleep tonight, think about the huge, white continent at the bottom of our world that holds its secrets under miles of old ice. Antarctica is still one of the great frontiers of human knowledge, whether those secrets are hidden civilizations or just undiscovered ecosystems, minerals, and geological wonders. The ice continent teaches us to be patient by showing us that some mysteries take decades or even centuries to unfold. The Antarctic ice sheet has been growing for millions of years, layer by layer. It not only keeps old climate and weather data safe, but it may also hold other secrets that we haven't yet learned how to find. In our fast-paced world of instant communication and quickly growing knowledge, it's very calming to think about places that are still a mystery. Antarctica lets us think about things that are just outside of what we know about science right now. The continent also serves as a reminder of how adaptable life can be. Antarctica shows that life can thrive even in places that seem impossible to live in. For example, the microorganisms in those hidden lakes and the penguins and seals that do well in the harsh surface conditions. This resilience indicates that the potential for life, whether straightforward or intricate, surpasses our initial perceptions. The most valuable aspect of contemplating hidden Antarctic civilizations may not be their actual existence, but rather what the possibility reveals about human adaptation, creativity, and survival. From the Arctic tundra to desert oases to high mountain valleys, human societies have always been able to adapt to very harsh environments. Each of these adaptations necessitated not only physical survival, but also the formulation of entirely novel paradigms for comprehending and interacting with the environment. People who lived in the Arctic learned a lot about ice and weather patterns, which helped them survive in conditions that would quickly kill outsiders. People who lived in deserts learned how to find and save water sources that other people couldn't even see. Mountain cultures learned how to live at high altitudes, where the air itself seems too thin to support life. An Antarctic civilization would exemplify the pinnacle of adaptation, necessitating the creation of technologies, social structures, and epistemologies unprecedented in human history. Whether this kind of society exists or not, thinking about its possibilities makes us think outside the box and reminds us of how creative and adaptable humans can be. There are thermal springs and geothermal vents under the ice in Antarctica that make pockets of warmth and liquid water in a world that is otherwise frozen. These natural oases, which are hidden from view, have the right conditions for complex life forms to live in. Recent discoveries of these features have shown that there are ecosystems that don't depend on surface conditions at all and get their energy from chemical processes instead of sunlight. These discoveries have completely changed what we know about the limits of life on Earth and opened up new possibilities for life on other planets where the surface conditions seem hostile, but the subsurface environments might be more welcoming. If these conditions can sustain life and facilitate the evolution of complex organisms, then a theoretical basis exists for communities to emerge in total isolation from surface conditions. The sound properties of ice add another interesting layer to the mix. Sound moves through ice in ways that are very different from how it moves through air or water. These properties could be used to send messages over long distances. A civilization that grew up in such a place might become experts in acoustic engineering, figuring out how to send complicated messages through ice structures over hundreds or even thousands of miles. They may have figured out how to use the natural resonance frequencies of ice formations to make communication networks that go all the way across the continent, or they may have come up with ways to change ice structures so that they work as acoustic amplifiers or focusing devices. They might have a very advanced understanding of how sound interacts with different kinds of ice temperatures and pressure levels. Such a civilization would need to know how temperature affects the formation of ice. Different conditions make ice with different properties. For example, clear, hard ice forms slowly at constant temperatures, while complex crystalline structures form when temperatures change. A society that lived closely with ice for thousands of years would probably be able to explain these differences in much more detail than scientists can now. They may have learned how to grow certain types of ice for different uses, such as making building materials, tools, and even art from carefully controlled ice formation processes. Their buildings would be very different from what we know. They would have to work with the way ice expands and contracts naturally, the way glaciers move, and the way different types of ice change temperature. Living in such a controlled environment would have a big impact on society. An underground society in Antarctica would have to grow within strict limits on space and resources, unlike surface civilizations that can grow over large areas. This limitation would probably result in social systems that emphasize collaboration, efficiency, and sustainable resource utilization in manners that surface civilizations have seldom accomplished. In a society like this, conflict resolution would be very important because people wouldn't be able to just move away from disagreements like they can on the surface. They probably made advanced systems for dealing with social tensions and keeping peace in their small group. In such a civilization, education would prioritize different things than it does in our own. Instead of learning about geography, weather patterns, and the natural world that people who live above ground take for granted, they would learn how to read the subtle signs and conditions of their underground environment. They would have to learn how to read thermal patterns, understand how ice forms, and keep the delicate balance of their closed ecosystem. Their idea of exploration would also be very different. Instead of exploring landscapes horizontally, they would probably focus on vertical exploration, mapping the complicated three-dimensional shapes of caves, thermal vents, and ice formations that make up their world. They may have learned how to safely explore deeper into the Earth's crust by following geothermal sources and mapping underground water systems with amazing accuracy. In a civilization like this, time would be measured by things that are very different from the solar and seasonal cycles that control how we keep time on the surface. They might keep track of time by thermal cycles, the slow movement of ice formations, or other geological processes that happen on a different scale than surface phenomena. The complex rhythms of geothermal activity, the slow changes in ice pressure and formation, or even the small changes in the Earth's magnetic field that might be easier to see in their deep, isolated environment, could all be used to make their calendars. These different ways of organizing time would change how they think about history, planning, and the link between short-term events and long-term processes. As we come to the end of our deep thoughts tonight, it's worth going back to the main question. Does the idea of a hidden civilization in Antarctica matter, even if such a society doesn't exist? I think the answer is a big yes. Thinking about these kinds of things has a number of important benefits. First, it reminds us that our planet still holds deep mysteries, and that even with all the technology we have, we still don't know everything we need to know. This acknowledgement can cultivate intellectual humility, resulting in enhanced scientific inquiry, more deliberate decision-making, and a deeper appreciation for the intricacies of our environment. Second, thinking about other ways that human civilization could have developed helps us understand our own society better. We can better understand the choices our own civilization has made, the paths we've taken, and the options that might still be open to us by thinking about how people might change in very different situations. Third, such conjecture can stimulate genuine scientific investigation. Many significant discoveries have originated from theoretical inquiries that initially appeared entirely fictitious. The search for extremophile organisms, the study of subglacial lakes, and the creation of technologies for exploring hostile environments all start with the kind of creative questioning that asks, what if, instead of what is? The secret. Civilization in Antarctica is a symbol of all the things we don't know yet that could happen. Whether those possibilities include undiscovered life forms, unknown physical processes, or just new ways of looking at things we think we already know, they remind us that reality is always more interesting, more complicated, and more amazing than our theories suggest. Antarctica is a perfect example of this idea. Researchers are always surprised by what they find on this frozen continent, which helps us learn more about what's possible on Earth. Antarctica keeps showing us that even our own planet has secrets we never knew about. For example, it has subglacial lakes with ancient, isolated ecosystems and active volcanic systems beneath the ice. The continent is also a place where scientists can learn about how life might exist on other planets. The conditions below the Antarctic ice are very similar to those that might exist on Mars, on the moons of Jupiter and Saturn, or on other planets where the surface seems hostile, but the subsurface might be more welcoming to life. Scientists are learning more about the possibilities for life throughout the universe by studying how organisms survive and thrive in Antarctica's harsh conditions. If a complex civilization could theoretically grow up in the isolation beneath Antarctic ice, then the possibilities for life and intelligence elsewhere in the cosmos become correspondingly broader and more intriguing. As you get ready for bed tonight, no matter where you are in the world, think about the huge white continent at the bottom of our planet that has been hiding its secrets for thousands of years under miles of ice and snow. Antarctica is still one of the most important places for people to learn about the world. It may hold secrets about hidden civilizations, undiscovered ecosystems, or just new ways of understanding how our planet works. The ice continent teaches us to be patient, curious, and humble when we don't know something. It reminds us that some questions take generations to answer, that some secrets take a long time to come out, and that the most interesting discoveries often come from places and possibilities we never thought to look into. In this time when information moves quickly and people can talk to each other right away, it's very healing to think about mysteries that take time to unfold, secrets that need patience to find, and possibilities that are just out of reach of what we know and can do now. Antarctica is the perfect place for this kind of gentle mystery. It makes us wonder without needing answers right away, and makes us question without needing a solution right away. The frozen continent at the end of the world still keeps its secrets. It waits quietly under its ancient ice for human knowledge to slowly, carefully, and respectfully uncover whatever truths are hidden in its depths. Whether those truths encompass evidence of concealed civilizations or merely a newfound comprehension of life's extraordinary adaptability, they will undoubtedly be as intriguing and astonishing as all that Antarctica has unveiled regarding the intricate complexity of our world. Have sweet dreams, and may your sleep be full of the peaceful wonder that comes from thinking about the beautiful mysteries that still exist in our amazing world. During the long polar winter, the sun never really rises over most of Antarctica. Instead, it stays in twilight for months at a time, In this kind of place, the idea of day and night becomes vague, abstract, and almost meaningless. A civilization that grew up in these kinds of conditions would have a very different relationship with light than any society that has ever lived on the surface. They may have figured out how to make their own lights using ideas we haven't found yet. They may have come up with ways to capture and concentrate the little light that gets through ice, making optical systems that could gather and focus even the faintest light into usable brightness. Or maybe they learned to work without light at all, creating senses and technologies that work with sound, temperature, vibration, and other inputs that aren't visual. Think about how their understanding of colour would be different from ours. People who live on the surface learn to see colours by looking at the full range of sunlight, the changing colours of the sky and landscape, and the different colours of natural light throughout the year. An underground civilization in Antarctica might have had very different ideas about what is beautiful to look at. For example, they might have grown bioluminescent organisms for both practical and aesthetic reasons, or they might have noticed the subtle colour changes in different types of ice, or the faint glow of certain minerals. Their relationship with the seasons would also be very different. People who live on the surface plan their lives around the seasons of spring, summer, autumn, and winter. People who live underground, on the other hand, may be more in tune with much longer rhythms. The slow movement of glacial ice, the multi-year cycles of geothermal activity, or the gradual changes in underground water flows that might take decades to finish could all be used to tell time. This different way of looking at time would change everything about their society. If they grew crops, their agricultural cycles would be based on rhythms that are very different from those of surface farming. Their cultural and social events might happen every few years instead of every year. Their idea of how long people live and how generations change might be based on these longer cycles, which would give them views on continuity and change that we can hardly imagine. The materials science of a civilization like that would be amazing. They would have learned how to work with ice, stone, and minerals they could get from the ground in ways that are much better than what we know now. They may have figured out how to make composite materials out of ice and mineral fibers, and how to build things that use ice's unique properties instead of working against them. If they ever learned about metallurgy, it would be very different from ours. They might have learned how to get metals out of ores and clean them up using chemical processes that work at low temperatures instead of using fire to melt them. They might have found catalytic processes that we haven't thought of yet, or ways to change molecular structures that don't need the high-energy methods that are common in surface metallurgy. It would be interesting to think about how much medical knowledge a civilization like that would have. They would have developed completely different ways of providing healthcare and medicine if they lived in a place where some diseases couldn't exist and others were only present in their own conditions. They may comprehend the impacts of pressure fluctuations, temperature shifts, and restricted light exposure on human physiology in ways that could transform our medical understanding. Their understanding of psychology would probably be very advanced. Taking care of their mental health in a closed-off, isolated space would be very important for their survival. This would force them to learn how to stay mentally healthy in ways that people in more open societies have never had to. They could have deep insights into meditation, consciousness, and how the mind works that could change how we think about psychology and mental health. The math and physics that a civilization like this would come up with would probably be about things that surface science hasn't looked into much yet. They could come up with new branches of science by using their deep knowledge of crystalline structures, pressure dynamics, and thermal flow to make new mathematical discoveries. They may comprehend principles of matter and energy that remain undiscovered by us, as we have not investigated the particular conditions present in their environment. Their way of doing engineering would be very different from ours. Instead of making buildings that can withstand and overcome natural forces, they would probably make systems that work with and guide natural processes. They would build their buildings based on how ice flows, how thermal gradients create pressure differences, and how to use these natural forces to get things done. Transportation in this kind of civilization would be very different from what we know. They may have figured out how to get through ice by melting and refreezing it in a controlled way, making temporary paths that close behind them. Through their underground network, they could have learned how to use thermal currents and pressure differences to move people and things over long distances. Their environment would determine how their communication systems worked. Sound travels through ice differently than through air, and they may have come up with advanced ways to talk to each other over long distances using sound properties that we don't understand. They might have networks of ice formations that are strategically placed and act as acoustic amplifiers, letting complicated messages travel hundreds of miles. Their music would be very different from what people on the surface have made. They may have made instruments and music that make sounds that can't be made anywhere else by using the natural resonance of ice caves and the acoustic properties of different ice formations. They would have concert halls that were naturally formed ice caves with acoustic properties that took thousands of years to develop. The artistic traditions of a civilization like this would be totally new. They would use ice as a living, changing medium for their sculptures, making works of art that change over time as the temperature changes and the ice naturally changes shape. They may have figured out how to make permanent art by putting minerals and other materials into ice structures. This made works that combined the beauty of ice crystals with the durability of stone and metal. If they had any textile traditions, they would be based on materials we've never thought of. They may have learned how to work with mineral fibers, making fabrics from processed stone or metal that are strong and keep them warm in their own special way. Or maybe they came up with completely new ways to make protective and decorative coverings for the body. The philosophical traditions of an underground civilization would probably look into ideas that people in surface societies have never had to think about. What does it mean to live without limits? How does human consciousness adjust to living in fully enclosed environments? What kinds of spiritual experiences come up when the sky and weather that have shaped most religious traditions aren't there? They might have created ways to meditate and connect with their spirituality based on how closely they were connected to geological processes. Instead of thinking about the sky and stars, they might have found transcendence in the slow, powerful movements of ice and stone. The Earth itself, the deep forces that make the planet's core hot and move continents, and ice sheets slowly but surely, could be the basis for their idea of the divine. Their stories and books would talk about things we've never had a chance to talk about. Instead of stories about faraway places and epic journeys across the surface world, their stories might be about journeys inside, exploring consciousness and building communities that are in perfect harmony with their surroundings. Their heroes might be people who learned to work with geological forces, who figured out how to keep social harmony in small groups, or who learned a lot about how natural processes work. The way schools work in such a civilization would be very different from how they work in our own. Their students would not learn about geography in terms of surface landscapes. Instead, they would learn about the three-dimensional geography of cave systems, thermal patterns, and underground water flows. They might study geology with the same dedication that we bring to understanding how the stars move instead of astronomy. It would be interesting to see how they approach child development. How would kids grow and change in a place where the idea of outside isn't the same as it is for us? They might get better at thinking about space, understanding how three-dimensional relationships work, and picking up on subtle patterns in sound, temperature, and pressure that kids who live on the surface never learn to see. The games and fun things to do in such a society would be very different from what we know. Their sports could be based on finding your way through complicated ice formations, competitions that test your acoustic skills, or contests that test your knowledge of how heat and pressure work. The way their kids played would help them get ready for life in their own unique world and help them learn skills and ways of thinking that we can hardly imagine. Their views on aging and death would probably be very different from those of surface societies. In a place where resources are limited and carefully managed, they would need to come up with cultural ways to deal with the life cycle that respect elders while also meeting practical needs. They may have cultivated notions of sustained societal contribution that persist into advanced age, identifying mechanisms for senior community members to maintain their significance within their insular ecosystem. In such a society, the connection between people and the community would have to be close. People can live pretty independently in surface civilizations, but an underground civilization in Antarctica would need a lot of cooperation and interdependence to stay alive. This could lead to social structures that find a balance between personal freedom and group responsibility, which is something that surface societies have not done very well at. Their environment would limit their ability to innovate and develop new technologies, but within those limits, they could be very advanced. It would be important to look at each new technique or tool, not only for how useful it is right away, but also for how it would change the delicate balance of their closed system. This could lead to smarter and more sustainable ways of developing technology than the ones we use now. It would be interesting to see how such a civilization kept records and stored information. They would have to come up with new ways to pass on knowledge from one generation to the next if they didn't have paper or other traditional writing tools. They may have figured out how to use ice formations to store information, how to use crystalline structures as storage media, or how to create memory techniques that let them keep a lot of information accurate over many generations. Their laws and rules would probably be based on the idea of keeping peace in their closed space. When exile or physical separation doesn't work to solve a problem, other methods will have to be used. This could lead to advanced systems of mediation, restorative justice, and community healing that surface societies could learn from. The trade and economy of this kind of civilization would be very different from those on the surface. They probably came up with economic ideas based on circular resource flows, sustainable extraction, and long-term thinking about how to manage resources in a world where everything has to be recycled and nothing can be wasted. They might be able to help surface societies that are having trouble with environmental limits by sharing what they know about economics. Instead of the mostly two-dimensional way that surface civilizations organize their territories, they would do it in 3 dimensions. They would think about both vertical and horizontal space, and they would build their society around complicated networks of interconnected chambers, passages, and thermal zones instead of the flat areas that are typical of surface political organizations. It would be interesting to think about the military or defense traditions of such a civilization. What would they have to protect themselves from? Geological events, not people, may be their biggest threats. This could lead them to learn how to deal with avalanches, ice shifts, and thermal changes instead of traditional military skills. They might think that security is all about managing the environment and being ready for disasters. Their method of exploration would be very different from surface exploration. They would not go into unknown areas of the landscape. Instead, they would explore vertically, mapping deeper cave systems, following thermal sources to their sources, and slowly learning more about the 3-dimensional world beneath the ice. Some of their great explorers might be people who found new thermal vents, mapped cave systems that no one else knew about, or found ways to make their territory go deeper into the earth. In a society like that, the way work and free time are related would probably be very different from how they are in our society. The need for constant monitoring and maintenance of the environment may require everyone to do the important work of keeping their closed ecosystem healthy. However, this work may be more integrated into daily life than the specialized work patterns of surface societies. They would have festivals and celebrations based on things and rhythms that we don't have. They might celebrate the finding of new thermal sources, the successful completion of big engineering projects, or the anniversaries of important new ideas that made their lives better. In their own special world, they might plan their vacations around geological events, thermal cycles, or other natural events that mark the passage of time. The clothing and personal adornment customs of this civilization would have been shaped by the materials and environment they had. They may have figured out how to make pretty and useful clothes out of processed ice, mineral fibers, or other things that were available in their underground world. Their ideas about how to look good would probably be very different from those of surface fashion. Their food customs would be very interesting. Because they only had a few ingredients in their closed ecosystem, they probably learned advanced cooking methods that made the most of the flavor, nutrition, and variety of the crops they could grow in their geothermally heated chambers. There may be dishes and flavour combinations in their food that you can't find anywhere else on Earth. As we get closer to the quietest hours of the night, it's a good time to think about what we've learned together on this gentle journey of imagination. The idea of a hidden civilization in Antarctica is more than just an interesting idea. It helps us understand how adaptable and creative people are, and how many different ways conscious beings might organize their lives and societies. Whether or not such a civilization really exists under the Antarctic ice, or is just a figment of our imaginations, thinking about what it could be like helps us understand what it means to be human. It reminds us that the decisions our civilization has made, like spreading across the planet's surface, using fire, metal, and fossil fuels, and building cities that reach for the sky, are just one set of options that human consciousness could have. Chosen, Antarctica reminds us that our planet still has deep secrets, even though it sometimes seems like all the mysteries have been solved and all the territories have been mapped. Scientists are still finding new things on the huge continent at the bottom of our world, which is buried under miles of old ice. These discoveries surprise scientists and help us learn more about what is possible in very harsh environments. Antarctica has real features like subglacial lakes, unique ecosystems, and volcanic activity beneath the ice. These show that even in the most barren places, complex and interesting processes are still going on. Life finds ways to survive, geological forces keep changing the landscape, and natural systems keep delicate balances that we are only starting to understand. The most important thing we learn tonight is that there is still wonder and mystery in our world. In a time when information moves quickly and communication is instant, it can be very healing to think about questions that don't have quick answers, possibilities that are just out of reach of what we know now, and mysteries that take decades and centuries to unfold instead of minutes and hours. Antarctica shows us how to be patient. Its secrets come out slowly, and you have to study it carefully over a long period of time and respect the harsh conditions that protect its mysteries. The continent reminds us that some kinds of knowledge can't be rushed. Sometimes understanding requires the kind of careful observation and sustained attention that our fast-paced modern world often has trouble keeping up with. The ice continent also teaches us to be humble. Even though we've made a lot of progress in technology and can see into the farthest parts of space and figure out how matter works, we still don't know exactly what's under the ice at the bottom of our planet. This reminds us that reality is always more complicated and surprising than our theories say it will be. As you go to sleep tonight, no matter where you are in the world, take with you the gentle wonder we've shared. Remember that our world still has deep mysteries waiting to be found. The image of that huge white continent with its ancient secrets hidden under miles of clean ice should remind you of this. Whether these mysteries pertain to concealed civilizations, undiscovered life forms, or merely a deeper comprehension of the extraordinary processes that perpetually shape our planet, they exemplify the infinite potential of reality to astonish and please us. We keep the sense of wonder that makes life rich and meaningful alive by thinking about these things. The wind in Antarctica carries whispers of secrets that haven't been found yet, questions that haven't been answered yet, and possibilities that are just out of reach of what we know now. In the vast silence of ice and snow, deep mysteries are still waiting for people to slowly, respectfully, and patiently find out what truths they hold. May your sleep be filled with the calm wonder that comes from knowing that our beautiful world still has endless mysteries, endless possibilities, and endless reasons to be amazed by how complex and beautiful life is. If you will, picture yourself going outside on a clear night and gazing up at the stars. The crisp promise of changing seasons or the aroma of evening flowers is carried by the soft breeze as it brushes against your face. It's a delicate dance between our planet and the forces around us, the product of billions of years of cosmic choreography. However, something else is at work, something strong but unseen that envelops our world like a mystical hug. We're going to investigate what our world might have looked like if this silent guardian had never been created. This is Earth's magnetic field. Every facet of life, as we know it, is touched by this tale, which starts deep within the molten core of our planet and extends all the way to the very edge of space. We must first comprehend what we have in order to comprehend what we may have lost. Imagine Earth as a dynamic, living system, rather than the solid, immobile sphere we typically think of. The outer core of our planet, a churning sea of liquid iron and nickel heated to temperatures comparable to the Sun's surface, is located nearly 3,000 kilometers below the surface of your feet. This is not the static, tranquil center you may have imagined from drawings as a child. Rather, it is a place of perpetual movement, where molten metal currents swirl and flow in patterns that would make the most intricate river system appear simple in comparison. These currents don't flow at random. They are propelled by the rotation of the planet, the heating and cooling of materials, and the same forces that propel our planet through space. Something amazing occurs as this liquid metal moves. Magnetic fields follow electric currents where they start to flow. It's the same idea that powers a basic electromagnet on a planetary scale. This process, which scientists refer to as the geodynamo, has been generating the magnetic cocoon that envelops our planet for billions of years. This process has incredibly beautiful mechanics. The liquid iron in the outer core is convecting, meaning that cooler material sinks and hotter material rises from deeper levels. Earth's rotation complicates this convection, causing what physicists refer to as the Coriolis effect. Together, these forces produce spiraling currents that, like cosmic taffy being drawn and molded by unseen hands, stretch and twist the magnetic field lines. However, what if it hadn't? What if things had turned out differently in the early stages of Earth's formation? It's possible that the planet's composition was different when it formed, lacking the iron-rich core required to generate magnetic fields. Perhaps the delicate balance required for the geodynamo to establish itself had been upset by our early collision with the Mars-sized body that most likely formed our moon, which knocked our planet's rotation into a different pattern. The planet may have cooled too slowly or too quickly, obstructing the precise temperature gradients required for convection. Though there are many options, the outcome would have been the same: a world devoid of its magnetic shield. Let's take a trip back in time to the early days of our planet's history, billions of years ago. As the young world revolves through space, it receives the same warming light from our star, forms the same early atmosphere through volcanic outgassing, and goes through the same gradual cooling and material differentiation processes. However, something essential is absent. This alternate world is still vulnerable to the harsh realities of space, whereas our Earth has developed its protective magnetic envelope. A fictitious observer would not have noticed the difference right away. The planet would have resembled our own in those early eons, before life had taken root. The gases that would make up the first atmosphere, methane, ammonia, water vapor, and carbon dioxide, would have been ejected from volcanoes that dot the landscape. The first oceans would have formed as a result of comets and asteroids, bringing more water and organic materials. The primordial soup of possibility would have contained the essential components of life. However, there has always been a more violent side to our sun, that ostensibly kind source of warmth and light. The solar wind, a river of charged particles travelling at amazing speeds, is constantly streaming away from our star. These particles travel through space at speeds of up to 1,000,000 miles per hour. They are primarily protons and electrons that have been stripped from hydrogen atoms in the sun's corona. The solar wind is not consistent. It flows outward from our star like an unseen hurricane in streams and gusts, becoming weaker during quieter times and stronger during solar activity. Something lovely and protective occurs on Earth when these particles come into contact with our magnetic field. They are diverted, steered innocuously around our planet like water around a rock in a stream, or directed toward the polar regions, where they combine with our atmosphere to produce the auroras, which are dancing lights. The magnetosphere, a huge protective bubble that stretches tens of thousands of kilometers into space and far beyond our atmosphere is created by the magnetic field. There would be no such defense or soft rerouting of these cosmic bullets on a world devoid of magnetism. Rather, the solar wind would directly impact the planet's atmosphere, atom by atom and molecule by molecule. Unlike wind blowing across a field, this is not a gentle process. High-energy particles have the power to literally disintegrate atmospheric gases or provide enough energy to launch them completely into space when they collide with them. This process, known as atmospheric stripping, would have persisted for billions of years, day in and day out. You may be wondering just how important this process is. After all, our atmosphere appears to be so large and substantial. You are taking in air from an ocean hundreds of kilometers above your head that contains about 5 quadrillion tons of gas. A few escaping molecules shouldn't be a big deal, right? However, when measured across geological epochs, the gradual becomes catastrophic, and time has a way of making the impossible seem inevitable. In contrast to Earth's thick layer of air, Mars, our neighbour, only has a thin layer of atmosphere today. According to available data, Mars' atmosphere used to be considerably thicker, possibly thick enough to sustain liquid water on its surface for extended periods of time. Water once flowed freely across the red planet's surface, according to ancient riverbeds etched into Martian rock. However, early in its history, Mars lost the majority of its magnetic field, most likely as a result of its smaller size and faster cooling, which stopped the convection processes in its core. The solar wind gradually but surely eroded most of Mars's atmospheric shield over geological time, possibly hundreds of millions or even billions of years. Any human visitor would require a pressure suit to prevent their blood from literally boiling in the low-pressure environment, as what is left today is less than 1% as thick as Earth's atmosphere, so thin that liquid water cannot exist on the surface under normal circumstances. The story would have been even more dramatic if our hypothetical Earth had taken a similar course. Because Earth is nearer the Sun than Mars, the solar wind is more powerful and persistent here. There are more particles per unit area, and they arrive with more energy. In the absence of magnetic shielding, the atmosphere of our planet would have been subjected to a more severe and prolonged attack than Mars has ever encountered. The process would have taken hundreds of millions, if not billions of years to develop. However, the atmospheric layer covering our planet would have gotten thinner and thinner over time, unavoidably. Only the heaviest molecules, and those that could somehow find refuge in the planet's gravitational well, would have remained after the thicker portions of the atmosphere were removed first. Even these may eventually have been destroyed by the unrelenting sunbeams. Let us now take a moment to reflect on the implications of this for the possibility of life. You're experiencing conditions that rely solely on the existence and density of our atmosphere. If you're reading this from a cozy spot tonight, maybe with a hot cup of tea close by or the gentle sound of rain hitting your windows, the reason for the comfortable temperature you're experiencing is that our atmosphere retains heat from the sun, avoiding the drastic temperature fluctuations that would happen in a world without air. For billions of years, photosynthetic life, organisms that could only flourish because our atmosphere offered the stable conditions they required, produced the breathable oxygen in the air you're breathing right now. Enough atmosphere is necessary to trap heat, move air masses, and establish the stable conditions necessary for life. This includes the protective barrier against the vacuum of space and the moisture distribution that produces weather patterns and allows rain. Without enough atmosphere, our alternate Earth would have changed drastically, possibly taking on the characteristics of a hybrid of our own Moon and Mars. There would have been abrupt and severe temperature changes. The day side might have gotten extremely hot, and the night side might have gotten extremely cold if there hadn't been air to disperse heat around the planet. Without wind patterns distributing temperature and humidity across continents, clouds collecting moisture from the oceans and transporting it inland, and the protective ozone layer filtering harmful radiation from space, weather, as we know it today, would not have existed. It is possible that the idea of seasons, those soft rhythms that signal the passing of time and serve as the setting for so much of the drama in life, would never have come into being. Only the harsh contrast between the furnace of day and the freezer of night would exist, tempered only by the thin wisps of atmosphere that might occasionally gather in the deepest valleys or craters, rather than the slow warming of spring or the crisp promise of autumn. This is where, however, our story takes its first intriguing turn. Life is incredibly resilient and inventive, as we have repeatedly found in the most unexpected locations on our own planet. Life may still have found a way to start on this magnetically barren Earth. The conditions under which the earliest life forms on our planet evolved would be fatal to the majority of living things today. In the crushing depths of the ocean, where no sunlight ever reaches, in environments with little to no oxygen, in scorching hot springs that would instantly kill modern organisms, in conditions so harsh that we refer to the creatures that inhabit them as extremophiles, lovers of the extreme. These early life formers didn't require the cozy surroundings that sophisticated life demands. They were straightforward, resilient, and highly adaptive. Others consumed the chemical energy emitted by volcanic eruptions. The radiation that would kill more complex organisms was a source of life for others. Many could endure extremes in salinity, acidity, temperature, or pressure that would denature the proteins of more complex organisms. On our alternate Earth, life might have sought refuge underground, where atmosphere and pressure could still be sustained. Imagine extensive underground networks of caverns and caves that have been sculpted over millions of years by volcanic and water processes. Here, pockets of atmosphere could be trapped and shielded from the relentless stripping of the solar wind. Kilometers below the hostile surface, geothermal energy from the planet's core could supply warmth and chemical energy for life processes, while the rock above would act as a shield against cosmic radiation. By our standards, these subterranean ecosystems would have been completely alien. They could not have evolved photosynthesis as we know it if they had no access to sunlight. Rather, they may have developed around chemosynthesis, which uses chemical reactions involving gases and minerals that leak from the planet's interior to produce energy. Consider the creatures that live near deep-sea volcanic vents today. These creatures have never seen sunlight and have based their entire ecosystem on the chemistry of dissolved minerals and heated water, bacteria that break down hydrogen sulfide, organisms that flourish in water hot enough to melt lead, and tube worms that grow meters long without ever consuming anything we would consider food. Such societies may have made up the entire population of our alternate Earth, surviving in the shadows and flourishing in the depths, forming a secret biosphere that stretched around the world via interconnected networks of caverns and subterranean waterways. Over the billions of years that these communities had at their disposal, they may have expanded to enormous size and complexity, creating complex food webs that relied solely on the cycling of minerals and chemical energy. Imagine, if you will, enormous subterranean lakes that are warmed by geothermal springs and have mats of vibrant bacteria growing along their shores, producing planetary abstract art. Living organisms may have created the mineral formations that line cavern walls, obfuscating the distinction between geology and biology. It's possible that strange chemical processes generate their own bioluminescence, giving the subterranean landscape an unearthly glow that has no names in our language. The bubble and gurgle of geothermal springs, the faint chemical hiss of mineral precipitation, and the distant sounds of vast microbial communities going about their ancient business are just a few of the sounds that may reverberate from these underground realms. The world would be more subdued and quieter than ours, but it would still be vibrant despite its differences. However, this begs the intriguing question: was it ever possible for complex life to arise from such lowly origins? The invention of photosynthesis marked a significant turning point on our planet. About 3 billion years ago, cyanobacteria discovered how to use sunlight to feed themselves. They also started releasing oxygen into the atmosphere, which drastically altered the chemistry of our planet and allowed for the emergence of more complex oxygen-breathing life. Since oxygen was poisonous to the anaerobic organisms that dominated early Earth, this event, sometimes referred to as the Great Oxidation Event, was actually disastrous for the majority of life forms at the time. But compared to their anaerobic cousins, organisms that were able to adjust to the new oxygen-rich environment had access to a lot more energy. The energy budget required for complex, multicellular life is provided by oxygen-based metabolism, which is about 15 times more efficient than anaerobic processes. This photosynthetic revolution would never have happened, at least not globally, on a planet without a surface atmosphere. It's possible that tiny communities of life close to subterranean water sources have evolved strategies for making use of the scant light that seeps through crevices and cracks. However, it would not have been possible for the enormous, revolutionary explosion of oxygen production that changed our planet. This implies that our alternate world would have lasted far longer than the billion years or so it took for our planet to form, probably remaining in a state similar to Earth's earliest biological era, which was dominated by simple microorganisms. Multicellular life, complex cells with nuclei, and the explosion of diversity found in the fossil record on Earth could have all been forever postponed or never occurred. However, there is a certain beauty in envisioning these subterranean worlds evolving into complex entities of their own. Evolution might have followed more patient, subtle paths if photosynthesis hadn't given our planet its energy windfall. Even though they didn't resemble our familiar plants and animals, these microbial communities may have evolved forms of organization and cooperation over billions of years that we would consider complex. Imagine underground networks of microbial colonies that cover entire continents and communicate via chemical signals that pass through rock formations and groundwater. It's possible that these planetary organisms have evolved memory and learning systems, storing environmental information in the patterns of their chemical networks. By relocating resources and population centers in response to minute variations in temperature, pressure, and chemical composition that signal earthquakes or volcanic eruptions, they may have developed the capacity to anticipate and prepare for geological events. Let's now go back in time to our alternate Earth and investigate what might have transpired as the planet continued to undergo geological reshaping. More than just atmospheric retention and the emergence of life would have been impacted by the loss of our magnetic field. The relationship between our planet and space itself would have been drastically changed, with ripple effects that would have affected everything from the surface geology to the planet's rotation. The upper atmosphere and surface of our planet would have been continuously bombarded by charged particles from the solar wind if there had been no magnetosphere to deflect them. It wouldn't have been a gentle bombardment because these particles are very energetic and can alter the chemical and physical composition of surface materials or molecules in the atmosphere. This bombardment may have gradually changed the planet's spin over geological time. The motion of objects in space can be affected by the solar wind's subtle but enduring force, which physicists refer to as radiation pressure. This force is mostly repelled on a planet shielded by a magnetic field. However, on our alternate Earth, the solar wind's constant pressure may have served as a cosmic brake, slowing the planet's rotation over billions of years. At first, this effect would have been extremely subtle, possibly slowing down each day by a few microseconds annually. However, these small changes would have added up over the long periods of geological time. It's possible that our alternate Earth's days were significantly longer than ours, and that it rotated so slowly that by our standards, the cycles of day and night lasted weeks or months. It's possible that the planet eventually became tidally locked to the Sun, displaying the same face to our star in the same way that our moon does to Earth. A world with perpetual day on one side and perpetual night on the other, with only a small twilight zone in between, where conditions might still be mild enough for life to survive, would result from this. Without night to provide cooling relief, the day side of such a world would have turned into a furnace, baked by the sun's unrelenting rays. It's possible that surface temperatures reached hundreds of degrees, which would have melted metals and evaporated any water that remained. Any lingering atmosphere might have frozen solid and turned to snow on the night side, which would have been the opposite extreme, a place of unending cold. However, there may have been a small area where temperatures stayed moderate along the terminator, which is the line that separates day from night. This twilight zone, which may have been hundreds of kilometers wide, and where the last remnants of the atmosphere may have gathered, where liquid water may still exist, and where life may have made its last stand above ground, may have developed into the planet's most biologically active region. As this habitable zone gradually moved as a result of minute changes in the planet's rotation and orbit, picture the enormous migrations of organisms that followed. The terminator line would have strayed across the surface over millions of years as the planet's position was subtly altered by gravitational interactions with other planets, and life would have had to adjust to this cosmic nomadism. It's possible that these terminator ecosystems evolved amazing survival techniques. Maybe they would have developed the capacity to quickly hibernate or insist when the environment got too harsh, awaiting the return of the habitable zone. Perhaps they would have acquired extraordinary mobility, enabling them to move between continents by adhering to the limited range of temperate conditions. Utilizing the energy differential between hot and cold areas, some may have evolved the capacity to flourish in the harsh temperature gradients at the boundaries of the habitable zone. Our alternate Earth surface geology would also provide a very different picture. In addition to shielding the atmosphere, our planet's magnetic field influences the way cosmic radiation interacts with materials on the surface. In the absence of this defense, cosmic rays, high-energy particles from deep space that can pierce deep into solid matter, would have continuously bombarded our alternate world. This cosmic bombardment would have significantly altered the rocks and minerals on the surface over geological time. Cosmic rays have the power to change crystal structures, produce new isotopes, and initiate chemical reactions that would not normally take place. Our alternate Earth's rocks may have acquired distinct compositions and characteristics, including isotopic signatures, that reveal the effects of exposure to cosmic radiation over billions of years. It's possible that these radiation-modified minerals produce landscapes that are unlike anything found on our safe planet. They might have produced surfaces that shimmer and glow with internal light by forming crystals with peculiar optical characteristics. Perhaps complex organic molecules would have formed in rock formations due to the continuous radiation, resulting in a type of geological life that exists at the intersection of biology and chemistry. Meteoroids that would typically burn up in our atmosphere would reach the surface undamaged if there was no atmospheric shield. The accumulation of impact craters over billions of years would produce a landscape that resembles the Moon or Mars more than the Earth as we know it. However, our alternate Earth would still have been experiencing geological activity, such as earthquakes, volcanic eruptions, and the gradual drift of continents, in contrast to those worlds. It's possible that impact cratering and continuing geological processes combine to produce genuinely alien landscapes. Imagine enormous crater fields inside old impact basins where new mountains have been formed by volcanic eruptions. Imagine deep canyons filled with the odd radiation-altered minerals that tell the tale of cosmic bombardment, where the planet's crust has broken apart to form rift valleys. Since there wouldn't be any wind or rain to erode these craters away, they would stay pristine for a lot longer than they would on Earth. Every strike would leave a lasting mark on the terrain, a record of cosmic occurrences spanning billions of years. For short geological periods, surface life may have persisted in isolated pockets created by the largest craters turning into deep basins where any leftover atmosphere could gather. However, the idea of life continuing on such a planet has a deeply poignant quality. life would find a way to not only survive, but also to flourish and evolve in the face of overwhelming odds and in environments that appear to be hostile to everything we know about biology. It serves as a reminder that the creativity of life transcends our earthly experience and that there may be forms of existence in the universe that we have never imagined. Let's think about what might have happened if our planet, which lacks a magnetic field, had managed to hold on to enough atmosphere to sustain surface water, at least in some areas. The planet may have been able to retain more of its atmospheric blanket in spite of the solar wind's attack because of its larger size than Mars, a different atmospheric composition, or the shielding effect of a particularly strong greenhouse effect. We could envision a world of stark extremes and contrasts in this scenario. In the deepest basins, the surface may be dominated by huge shallow seas, shielded by whatever thin atmosphere was left. Due to billions of years of evaporation under intense solar radiation, these seas may be extremely saline. These waters' chemistry would be completely different from that of the oceans on Earth today, possibly full of dissolved minerals and other substances that complex ecosystems have never had a chance to process. Compared to the comparatively fresh waters of Earth's oceans, the salinity of these seas may be so high that they resemble liquid mineral deposits. However, life's extraordinary tenacity may have allowed it to flourish despite these extremely salinized conditions. Some living things on Earth already survive in extremely salinized environments, such as salt lakes, subterranean brine deposits, and the saltiest parts of our oceans. It's possible that life in these extraterrestrial waters took on nearly crystalline forms, creating complex structures out of the many minerals dissolved in the extremely salinized environment. These organisms have the potential to create enormous living reefs composed of both biological material and precipitated minerals, obfuscating the distinction between living tissue and geological formation. They may have developed the ability to manipulate mineral precipitation, creating structures and shells out of dissolved salts with such accuracy that human engineers would be envious. Such a world, with its surface painted in colours that have no corresponding hues in the earthly palette, might seem to sparkle and shine with an unearthly beauty from space. Unusual light reflection from the hypersaline seas could produce crystalline landscapes that shimmer. Large salt flats that stretch to the horizon, where these seas met the land, may have been covered in mineral deposits and resilient microorganisms that gave them their vivid hues. The continents may have been left as huge empty stages for purely geological dramas due to the absence of complex land life. Without animals to mix and disturb sediments and plants to break down rock and produce soil, the landscape may have stayed mostly the same for billions of years. It's possible that old mountain ranges remain intact, untouched by the erosion that shapes the surface of our planet. Canyon systems of amazing size and geometric accuracy could be formed by rivers, if there were any, cutting deep, straight channels through bedrock. Without the biological cycles that mold the surface of our planet, these geological processes would have continued to function. There wouldn't be a nitrogen cycle fueled by bacterial activity, an oxygen cycle sustained by photosynthesis, or a carbon cycle powered by living things. Rather, geological processes such as volcanic outgassing, mineral weathering, and chemical precipitation would be the only factors influencing the chemistry of our alternate Earth. This may have eventually produced chemical environments that are entirely different from what we're used to. Unusual chemical compounds that only form under particular temperature, pressure, and radiation exposure conditions might have taken over some areas. Forms of life that use completely different biochemistries from anything on Earth may exist in these chemical landscapes. These organisms may breathe sulfur compounds, metabolize metals, and construct their cellular structures from minerals rather than organic molecules. The quiet of our alternate Earth, however, might be its most poignant feature. The sounds of life are all around us, the rustle of leaves in the wind, the the distant crash of waves formed by tidal forces influenced by marine ecosystems, the choruses of insects in the summer evenings, and the songs of birds that greet each dawn. We hardly ever notice these sounds because they are so ingrained in our daily lives, but they are the manifestation of billions of years of evolutionary creativity expressed through rhythm and vibration. In the absence of complex surface life, our alternate world might only be familiar with the sounds of geology, the crack of thermal expansion and contraction as surface materials heat and cool with the extremes of day and night, the whistle of thin wind across desolate landscapes, the crash and hiss of volcanic eruptions, and the rumble of earthquakes as tectonic plates shift and grind against one another. However, there may be sounds we have never heard before in the depths, in those safe underground worlds we previously envisioned. The faint vibrations of vast microbial communities going about their ancient business, the bubble and gurgle of geothermal springs, and the subtle chemical hiss of mineral precipitation. These would be the hints of an alternative existence, one that is just as real despite being outside of our experience. These subterranean ecosystems may have evolved their own acoustic communication systems. Imagine a planetary nervous system that spans continents with microbial communities communicating via chemical signals transported by subterranean water systems. A sort of geological music that narrates the persistence of life in the deep may be produced by the patterns of these chemical communications. Our alternate Earth's interaction with cosmic forces may have produced intriguing effects as it grew older, and its relationship with space continued to change. Without a shielding magnetic field, cosmic radiation and the solar wind could have interacted directly with the planet's surface and any lingering atmosphere, changing the planet's physical characteristics over time. These interactions may have led to complex changes in the planet's rotation over geological time. In addition to providing a basic braking effect, the solar wind's intensity fluctuates with cycles of solar activity, producing recurring forces that may cause the planet to wobble or alter its axial tilt. On our stable, magnetically shielded planet, these changes may have produced intricate climate patterns unmatched by anything else. Imagine a world in which the distribution of solar energy across the surface undergoes drastic changes due to significant shifts in the axis angle over millions of years. Once moderate regions could turn into extreme ones, and once uninhabitable areas could momentarily turn into oases of mild weather. If life continued on such a world, it would have to be extraordinarily adaptive in order to endure both the gradual changes that take place over geological time, as well as the sudden environmental extremes. It is possible that these axial variations gave rise to what we might refer to as geological seasons, million-year intervals during which the world's conditions gradually changed from one extreme to the other. There may be brief periods during which ice may form at the poles, and moderate conditions may spread farther from the equatorial regions due to the planet's tilt during some epochs, which causes more solar energy to reach the polar regions. The planet may tilt more sharply in other eras, focusing solar energy at the equator and intensifying the polar regions. It's possible that organisms that have adapted to such a world have developed amazing survival mechanisms for these geological seasons. It is possible that some species have evolved incredibly long lifespans, surviving several axial shifts. Others may have developed the capacity to go into suspended animation for millions of years in order to wait for the right circumstances to reappear. As climate zones gradually change due to the shifting axial tilt, still others may have developed extraordinary mobility and migrated across continents. It's possible that special atmospheric chemistry was produced by the interaction of cosmic radiation with any residual atmospheric gases. High-energy particles would continuously interact with atmospheric molecules in the absence of a strong magnetic field, causing chemical reactions that wouldn't normally take place. Unusual compounds that are absent from Earth's protected atmosphere may have been produced by these reactions. Life may have benefited from some of these radiation-induced chemical reactions. They might have produced intricate organic compounds that organisms with the necessary adaptations could use as nutrients. Perhaps the steady stream of cosmic radiation would have pushed atmospheric chemistry in ways that would have made the environment more conducive to some forms of life. But let's put these hypothetical situations aside and think about what would have happened to one important part of the history of our planet. The evolution of consciousness and intelligence had Earth's magnetic field not existed. In addition to billions of years of evolution, exceptionally stable conditions over extended periods of time were necessary for the transition from simple microorganisms to sophisticated, thinking beings. Consistent environmental conditions that permitted the slow accumulation of biological complexity were necessary for the development of sophisticated nervous systems and brains with consciousness, reasoning, and self-awareness. From basic reaction mechanisms to sophisticated sensory systems to abstract reasoning, every stage of the development of intelligence built on the one before it in a convoluted chain of ever-increasing complexity. With its thin atmosphere, high radiation levels, sharp temperature fluctuations, and ever-changing environment, our alternate Earth may never have offered the stable environment required for this type of slow evolutionary development. Instead of permitting the type of experimental complexity that ultimately resulted in consciousness on our planet, the ongoing environmental stress may have kept evolution concentrated on basic survival. Complex brains require a tremendous amount of energy. Even though they only make up around 2% of our body weight, human brains use 20% of our metabolic energy. Only in an environment where organisms can consistently obtain enough nutrients and are not required to allocate all of their resources to immediate survival needs is this type of energy budget feasible. It's possible that the energy requirements for survival on our hostile alternate Earth were so great that evolution was never able to experiment with energy-intensive organs like sophisticated brains. Basic survival, protecting cellular structures from radiation damage, and adjusting to ever-changing circumstances would have required every calorie. The rarity of intelligence in the universe is called into serious question by this. Perhaps Earth-like intelligence is much less common than we might think if complex life and consciousness require stable, protective magnetic fields to develop. Simple life may exist throughout the universe, with planets supporting enormous ecosystems of microorganisms and possibly simple multicellular creatures. But the particular circumstances required for beings to be able to reflect on their own existence may be incredibly rare. Scientists use the Drake equation, which accounts for both the evolution of intelligence and the emergence of life, to calculate the probability of intelligent life in the universe. The likelihood that any planet could produce sentient beings would be greatly diminished if protective magnetic fields were a necessary condition for the emergence of intelligence. It's possible that the universe is much more isolated than hopeful estimates indicate. However, this story also offers cause for wonder and hope. It implies that biology is far more inventive and adaptive than we occasionally think if life could find ways to flourish in the hostile environment of our alternate Earth. Perhaps entirely different evolutionary pathways could give rise to intelligence, evolving in ways we haven't thought of. Eventually, the enormous microbial communities of the subterranean ecosystems of our alternate world may have developed networks of coordination and communication that span entire planets and are identifiable as conscious, even if they don't resemble our own individual minds. It is possible that these planetary intelligences perceive the world in ways that are entirely different from our own embodied consciousness. They may experience thoughts that develop over millions of years, thinking in geological time. The chemical structures of old rock formations, which act as a sort of mineral library, may contain forms of memory that date back to the early days of the planet. They may find beauty and significance in patterns of subterranean water flow that span continents, and they may dream in the language of mineral precipitation and thermal cycling. Our values and concerns may differ greatly from those of such intelligences. They may think in terms of planetary stability and chemical balance, whereas we think in terms of individual survival and reproduction. Where we produce music and art, they may produce intricate mineral deposition and chemical cycling patterns that convey aesthetic qualities we can hardly fathom. They could send messages through the planet's hydrological systems at speeds that would appear glacially slow to us but are entirely normal to creatures that measure time in geological epochs. They could do this by subtly altering the chemistry of the groundwater. Their discussions could go on for thousands of years, delving deeply and patiently into philosophical issues regarding the nature of existence that would be impossible for individual minds to accomplish. Through their planet's reactions to gravity, these planetary minds may have eventually developed an awareness of the universe outside of their own, picking up on the rhythms of celestial mechanics. They may have formed a science based on emotion and intuition rather than outside observation, gaining a profound understanding of physics and astronomy via first-hand experience of how cosmic forces impact their environments. It's important to consider what this thought experiment tells us about our own world and our place in the universe as we draw to a close our exploration of the potential history of this alternate Earth. Because it is so completely dependable, it is easy to take for granted the invisible, intangible magnetic field that envelops our planet. For billions of years, it has been keeping us safe by silently and continuously preserving the circumstances that allow us to exist. This invisible guardian is responsible for every breath you take while listening to this, every instance of stable weather you've ever had, and every sunset you've ever savoured. Because of the ability of our atmosphere to retain and disperse heat, your room is currently at a comfortable temperature. Our magnetic field kept the atmospheric conditions necessary for photosynthetic organisms to flourish for billions of years, which is how the oxygen in your air was created. We also have a very complex and dynamic magnetic field. It is a complicated, ever-evolving pattern of magnetic force lines that shift and change over time, rather than a straightforward dipole like a bar magnet. Over decades, the magnetic poles can shift hundreds of kilometers. Regional variations in field strength result in magnetic anomalies that impact everything from satellite operations to compass readings. At times, our magnetic field becomes much weaker, and very infrequently, maybe once every few 100,000 years, it reverses entirely, turning magnetic north into magnetic south and vice versa. Earth's protection is momentarily diminished, but never completely removed, during these reversal periods, which can extend for thousands of years. Although the exact relationship is unclear, fossil evidence indicates that some of these reversals have occurred during times when extinction rates have increased. Even though our planetary defense system has proven to be dependable, these natural variations serve as a reminder that it is not static or permanent. In order to comprehend the past of our planet and to get ready for any future changes, scientists closely examine these changes. Although magnetic field reversals usually take thousands of years to occur and do not immediately endanger life on Earth, there is some evidence that we may be in the early stages of one right now. Our magnetic field would only weaken and reorganize into a more complex pattern before finally settling into the reversed orientation. So even during a reversal, it wouldn't completely vanish. However, the fact that this system on which we rely so heavily is undergoing change and evolution over geological time is a sobering reminder. The interdependence of the planetary systems that enable our world to support life is another point of emphasis in the tale of our alternate Earth. Scientists are still trying to figure out how the magnetic field, atmosphere, oceans, climate, and life itself are all closely related. Everything else reacts and changes when you make a big change to one component. The intricate interactions between numerous systems, each of which supports and reinforces the others, are what make Earth habitable rather than any one element acting alone. This viewpoint is especially pertinent as we think about the future of our planet and our responsibility as its temporary stewards. Numerous systems on Earth are being altered by human activity, including the stability of the climate, the diversity of life, the chemistry of the oceans, and the atmosphere. Although the magnetic field is beyond our control, we do have some control over many of the other systems that keep our planet habitable. We can better appreciate the value and fragility of the conditions we enjoy when we consider how different these systems may have been. Beneficial feedback loops and lucky coincidences over billions of years have created our cozy, stable environment. It is a remarkable convergence of cosmic circumstances that we exist at all as conscious beings with the ability to think about these questions. Visible indicators of our magnetic field in action are the aurora borealis and aurora australis, those dancing curtains of light that adorn our polar skies. Photographs or videos of these ethereal displays show how the solar wind and the magnetic shield of our planet intersect. These lovely lights are produced by the same particles that would otherwise be destroying our atmosphere, but our magnetic field turns them into works of art that are painted across the sky. These auroras happen when particles from the solar wind collide with gases in the upper atmosphere's thin air, guided by our magnetic field lines. When these particles hit oxygen atoms, they release red and green light. Blue and purple colours are produced by nitrogen. The intricate, dynamic structure of our magnetic field, as it reacts to changes in the solar wind, is reflected in the forms and motions of auroral displays. The sky would not be so beautiful on our alternate Earth. Perhaps the harsh reality of unfiltered cosmic radiation reaching the surface will replace auroras. The faint glow of any residual atmosphere from continuous bombardment would be the glow of destruction rather than creation, the light of molecules being torn apart instead of momentarily energized and released. Nevertheless, we can draw inspiration from life's tenacity and inventiveness even when we imagine this more brutal world. Life finds ways to not only survive but also thrive in environments that would quickly kill more familiar organisms, as demonstrated by the extremophile organisms that flourish in Earth's most difficult environments, such as boiling hot springs, extremely acidic pools, the crushing depths of ocean trenches, and the radioactive zones surrounding nuclear reactors. The types of life that might arise on our alternate world could be modelled after these resilient pioneers of Earth's harsh environments. Certain bacteria can withstand radiation exposures thousands of times greater than those that would kill humans. Others flourish at temperatures high enough to cause metals to melt. Others inhabit chemical environments that are so corrosive that they would dissolve the majority of the materials we use on a daily basis. Imagine what kinds of life might develop in the genuinely harsh conditions of a world without magnetic protection if such organisms can survive in the comparatively mild, extreme environments of our protected Earth. By our standards, these organisms may develop biological processes that are almost magical, metabolisms that obtain energy from chemical processes we consider destructive, cellular structures that operate at temperatures that would vaporize organic molecules as we know them, and the capacity to repair radiation damage more quickly than it accumulates. These extreme organisms may have evolved into complex ecosystems unlike anything we have seen in our alternate Earth's billions of years of evolution, even without the abundance of energy that photosynthesis gives our planet. They might have evolved strategies of competition and cooperation that produce complex networks of interaction. All life on our alternate Earth would have continued to rely on chemical energy sources, such as the heat and chemical gradients produced by geological processes in the absence of photosynthesis. However, this does not imply that such a world would be any less complex than our own. It would simply be different. Rich, complex biological communities can exist completely without the presence of sunlight, as demonstrated by the ecosystems surrounding hydrothermal vents in the deep oceans of Earth. In addition to bacteria, These vent ecosystems are home to complex animals like fish species that are unique to Earth, giant tube worms, and unusual crabs. They establish their own food webs using only chemosynthesis, demonstrating that photosynthesis is not necessary for biological complexity. We might envision biological diversity on our alternate Earth that is comparable to or even greater than our own, but constructed on completely different foundations. Given that it would take billions of years for such chemosynthetic ecosystems to evolve, in a world like that, the rocks themselves would record the geological past in ways that may be much more dramatic than those found on Earth. The interaction between the planet's interior and surface may have produced mineral formations and geological structures that tell tales of cosmic bombardment, atmospheric loss, and chemical extremes if there had been no life to buffer and moderate chemical processes. Imagine rock formations with layers that document cosmic ray bombardment over billions of years, with each stratum providing a different perspective on the planet's exposure to space. A geological record of our star's behavior over cosmic time could be created by the isotopic signatures found in these rocks, which might provide information about the history of solar activity. In ways that our own magnetically shielded planet cannot, such a world could be a goldmine for learning about the long-term evolution of our solar system. Our alternate Earth surface minerals may have characteristics that almost seem like science fiction. It's possible that constant exposure to high-energy particles produced crystal structures that aren't found on our safe planet. Unusual optical, electrical, or magnetic characteristics of these radiation-forged minerals may have impacted the evolution of any living forms that came into contact with them. It's possible that some life forms have evolved to use these special minerals in their biological structures, resulting in organisms with characteristics and materials not found in Earth biology. Consider organisms that construct their shells from radiation-altered minerals that offer defense against cosmic rays, or creatures with crystalline components that endow them with extraordinary abilities to sense electromagnetic fields. The carbon cycle on our alternate Earth would have functioned very differently from ours if there had been no complex surface life. Living things are essential to the movement of carbon between the atmosphere, oceans, and rocks on our planet. Carbon dioxide is drawn from the atmosphere by plants and incorporated into their biological structures. A portion of this carbon is buried in sediments after they pass away, eventually creating deposits of fossil fuels. Our alternate Earth's atmospheric carbon dioxide levels would be solely regulated by geological processes, such as volcanic outgassing and chemical weathering of rocks, in the absence of this biological carbon cycle. Over geological time, this could have resulted in drastically different atmospheric compositions, possibly alternating periods of cooling that caused atmospheric gases to freeze out and fall to the surface, with periods of greenhouse warming that helped the planet retain more atmosphere. Geological epochs with drastically different conditions may have been produced by these long-term atmospheric cycles, possibly offering windows of opportunity when surface conditions improved and became more conducive to life. Liquid water may have been stable on a larger portion of the planet's surface during warm periods when a thicker atmosphere accumulated, enabling brief evolutionary radiations before the environment deteriorated once more. In contrast to the steady rise in complexity in our own world, such climatic cycles may have pushed evolution in quite different directions. Life on our alternate Earth may have undergone sporadic episodes of rapid evolution and adaptation, followed by protracted periods of dormancy or simple persistence, as opposed to gradual, continuous evolution. The planet's distinct atmospheric and magnetic history would also have had an impact on the relationship between our alternate Earth and its moon. By stabilizing Earth's axial tilt, the moon's tidal forces help avoid drastic fluctuations that could lead to disastrous climate shifts. However, the presence of oceans and atmosphere also contributes to the moon's tidal effects by generating the friction that progressively slows Earth's rotation and pushes the moon farther away. The Moon's evolution might have gone differently on a planet with a weak atmosphere and possibly no stable surface oceans. It might have stayed nearer the Earth, producing more powerful tidal forces that could have contributed to the longer-term maintenance of some geological activity. Alternatively, the Moon might have moved away faster in the absence of oceanic and atmospheric tides to generate friction, which would have lessened its stabilizing effect on the planet's rotation. The planet's long-term habitability may have been impacted by intricate feedback loops produced by these orbital dynamics. Variations in the Moon's distance would have an impact on the planet's interior tidal heating, which would change volcanic activity and atmospheric component outgassing. In the meantime, variations in the planet's rate of rotation would have an impact on the distribution of the planet's remaining thin atmosphere, as well as the patterns of atmospheric circulation. I hope these explorations are stimulating your thoughts if you're still traveling with me through space. If you like these in-depth explorations of alternate universes and cosmic what-if scenarios, please consider subscribing. There is so much more to discover in the fields of science and creativity. We might envision a number of different outcomes for our alternate Earth story as we contemplate its long-term destiny. One possibility is that, like our Moon, the planet may eventually lose so much of its atmosphere that it is airless. Any surviving life would be restricted to the deep underground, where geological processes could continue to sustain pockets of atmosphere. However, there is also a chance that the planet may eventually acquire a new type of stability. Maybe the remaining atmosphere would be so thin and made up of such heavy gases after billions of years of atmospheric loss that the rate of loss would drastically slow. When the rate of atmospheric loss equals the rate of outgassing from geological processes, the planet may achieve a new equilibrium. Perhaps made up primarily of noble gases like argon and xenon, which are less vulnerable to being removed by the solar wind, this equilibrium atmosphere could be very different from anything we are familiar with. An atmosphere like that might still be thick enough to support some life forms on the surface, but it would not produce much greenhouse warming and would be inhospitable to any of the known life forms. According to this scenario, our alternate Earth may eventually resemble a cross between Mars and Venus, too thin to sustain life on Earth, but thick enough to produce weather patterns and possibly sustain liquid water in some areas. The distinct chemistry of this exotic atmosphere may paint the surface with hues and formations that are unmatched in our solar system. Some of the most unusual life forms we can think of could develop in such a setting. The chemical reactions between surface minerals and atmospheric gases could provide them with energy. They may be able to endure conditions close to vacuum, perhaps spending a portion of their life cycles as airborne spores floating through the thin atmosphere, and another portion as organisms that live on the surface and are resistant to extreme temperatures and radiation. It's possible that these organisms have developed extraordinary senses and reactions to cosmic radiation, possibly utilizing it as a source of information as well as energy. They may be able to identify and decipher the minor changes in cosmic ray intensity brought on by solar cycles, seasonal shifts in Earth's orbit, and even the planet's journey through various galactic regions. Such organisms may acquire a far more profound understanding of astronomical cycles than humans over cosmic timescales. Their genetic material or behavioral patterns may contain information about galactic dynamics, stellar evolution, and the long-term changes in the environment of our solar system, making them living libraries of cosmic history. The most intriguing possibility for our alternate Earth, however, is that intelligence might eventually appear, albeit in a form so dissimilar from our own that we might not recognize it as consciousness right away. The subterranean microbial networks on the planet may eventually develop a level of collective intelligence that enables them to reflect on the nature of the universe and their own existence. Consciousness may be experienced by such a planetary mind in ways that transcend both global space and geological time. Its ideas could develop over millions of years, encoded in the gradual chemical alterations of ecosystems at the continental scale. The mineral structures of old rock formations may contain its memories, forming a kind of geological consciousness that retains knowledge of the planet's whole past. Eventually, this planetary intelligence may be able to perceive the universe outside of its own planet, detecting the gravitational pull of other planets, the shifting cosmic radiation intensity as the solar system passes through the galaxy, or even the minute impacts of far-off stellar explosions on the chemistry of its planet. Instead of the external observation that defines human science, it might create a science based on first-hand experience of cosmic forces. Individual minds like ours may have very different values and concerns than such a being. It may be more concerned with planetary stability and cosmic harmony than we are with our own personal survival and happiness. The orchestration of global chemical cycles and the creation of stunning mineral formations that span continents are two examples of how creativity can be expressed in literature and art. This planetary consciousness may eventually even discover methods to connect with the universe outside of its own world. It might be able to produce detectable signals by altering the magnetic field or atmospheric composition of its planet. It could use controlled variations in the planet's interaction with the solar wind or subtle changes in the planet's infrared signature to convey messages. A network of planetary minds exchanging information across interstellar distances could be formed if such intelligences were present throughout the universe. As patient and tenacious as the geological processes that gave rise to their consciousness, their communications may develop over millions of years. Their conversations, which are invisible to our instruments, but rich in meaning for minds that think in cosmic timescales, may be about the nature of existence and the meaning of the universe at this very moment. As we get ready to wrap up our exploration of this alternate history, let us pause to consider the incredible series of events that brought us into this world. The right planet's size to sustain liquid metal in its core, the right rate of cooling to establish convection currents, and the right rotation rate to produce the Coriolis effect required for field generation, all played a complex role in the development of Earth's magnetic field. Our world might have gone in the direction we've been envisioning tonight if any of these elements had been substantially different. Rather, by what appears to be a remarkable cosmic accident, our planet created and preserved the magnetic shield that allowed us to exist. Because of this protection, our atmosphere was able to stabilize and thicken. It created the conditions for photosynthesis to develop and change the chemistry of our planet. Over billions of years, it established the stable conditions necessary for complex life to develop, eventually giving rise to consciousness and intelligence. With its astounding diversity of ecosystems and life forms, it enabled the rich biosphere that envelops us today. Maybe you'll become more conscious of the unseen forces that guard and surround you as you fall asleep tonight. The magnetic field that envelops our planet like an unseen hug is responsible for everything, from the air you breathe to the steady temperature that keeps you comfortable to the shielding from cosmic radiation that keeps your cells functioning normally. Though it is based on actual science and real possibilities, our voyage through the alternate Earth has been a thought experiment. Mars serves as a reminder that planets can lose a large portion of their atmosphere and their magnetic shield. What can occur when atmospheric conditions drastically change over planetary timescales is demonstrated by Venus. In its stable, magnetically shielded state, Earth may be more unique and valuable than we frequently think. However, this story also contains wonder and hope. We have learned that life is extraordinarily inventive and persistent. Biology manages to adapt and flourish even under the most trying circumstances. There may be life forms in the universe that exist under circumstances we think are unthinkable, intelligence that arises through unimagined channels, and consciousness that perceives the world in ways that are entirely different from our own. We get hints of what might be possible elsewhere in the universe, from the extremophile organisms that flourish in the harshest conditions on Earth. Rich biological communities can arise without the need for sunlight, as demonstrated by the intricate ecosystems that surround deep-sea hydrothermal vents. The universe may be far more alive than our earthly perspective occasionally permits us to imagine, given the extraordinary adaptability and inventiveness of life on our own planet. One of the universe's most amazing accomplishments may be our own consciousness, our capacity to reflect on these issues and envision different planet histories. This chain of emergence, matter organizing into atoms, atoms into molecules, molecules into cells, cells into organisms, and organisms into beings with the ability to question their own existence, may be extremely uncommon in the cosmic context, or it may be more frequent than we think, simply taking on forms we haven't yet learned to identify. We are also reminded of the significance of the systems we frequently take for granted by the tale of our alternate Earth. Changes that appear minor in geological time, but significant in human experience, have the potential to upset processes that appear so stable and dependable, such as climate stability, atmospheric protection, and the cycling of elements between the atmosphere, oceans, and land. The tale of what Earth might have been without its magnetic field serves as a reminder of how valuable our current circumstances are, especially in light of the problems we face today with climate change and environmental disruption. Even though we can't control the magnetic field of our planet, we can still affect a lot of the other systems that keep our planet habitable. The kind of world we leave for future generations will depend on the decisions we make regarding conservation, technology, energy use, and land use. Our alternate Earth story teaches us that habitability is not a given because it depends on the intricate relationships between numerous systems, some of which are out of our control, but others of which are greatly impacted by human activity. Most significantly, our journey tonight serves as a reminder of the importance of imagination and curiosity in comprehending our place in the cosmos. We can investigate not only what is, but also what might have been and what might be thanks to science. We can better understand the forces that continue to shape our world and develop a greater appreciation for the path that led to our existence by imagining different histories for our planet. We will learn more about not only our own world, but also the possibility of life elsewhere in the universe by investigating the questions we have discussed tonight, such as the conditions necessary for life, the evolution of intelligence, and the interactions between planetary systems. We will be searching for the clues that tell us whether those far-off worlds have the kinds of defense mechanisms that allowed life on Earth to exist as we improve telescopes and more advanced methods for researching planets around other stars. Perhaps you can find solace in the soft, imperceptible embrace of our planet's magnetic field as you get ready for bed tonight. It had existed for a very long time before life appeared, and hopefully it will still provide refuge and protection for our planet long after human civilization has assimilated into its prehistoric past. There is a sort of cosmic tenderness in its silent, continuous work, the universe tending to itself, establishing safe havens where beauty and consciousness can blossom. Good night, and I hope you awaken tomorrow feeling even more awed by the unseen protectors who enable your life. We are all safely transported through the cosmic night toward whatever mornings lie ahead as the Earth continues to spin through space, encased in its magnetic cocoon. The magnetic field of our planet is a symbol of something valuable in a universe that can appear vast, cold, and uncaring. Stability, protection, and the patient maintenance of the conditions necessary for the existence of life, love, and consciousness. Take comfort in the fact that you're a part of a remarkable story, a story of planetary evolution and cosmic forces that brought you to this moment of awareness and wonder despite seemingly insurmountable odds. You live on a planet that has sustained life for billions of years, are composed of star stuff, are shielded by invisible fields, and are warmed by a nearby star. That is no small miracle in the vastness of the universe. I hope you'll keep learning about the amazing tale of our planet and its place in the universe, if this voyage through time and space has piqued your interest. Numerous opportunities exist for us to view the world from a different perspective and recognize the extraordinary nature of things we frequently take for granted thanks to science. Rest in peace, knowing that you are protected by forces you cannot see, but that are always looking out for you. Until we cross paths again in another investigation of the mysteries of the cosmos.